resist the temptations in real. So, but you should enjoy the day. So be brief, okay? Well, I was saying that Alessandro already did cover these topics, but if you have any questions, you can ask me. And we can also have arrange tool for the CBPF labs, especially this one. It's a little messy right now because there is we have an air conditioning problem, and they are starting a new one. So, but I can show you where all these experiments were performed. Okay, and also the other labs at CBPF and future labs as well. Well, we use this technique, the nuclear magnetic resonance. As Alexander said, we did lots of things with these kind of systems. It's a 2-qubit system, and the nuclear spins of hydrogen and carbon in this molecule can be easily controlled, and we did lots of experiments, which I believe they were pioneered in this field, and all of you know, more or less. And so, just for clarifying, we have the Zima interaction, which is applied. We have to usually apply a strong magnetic field along the Z direction. Okay, it's performed using a superconducting coil. It is cold and at a helium temperature, and we have to maintain at this temperature in order to maintain the field. It's around 12 Teslas in the lab, and so this is the main interaction of the system. However, the system, the 2 qubits are coupled through the exchange interaction through the electronic cloud. And you can have this, usually in this system, you have this, which is we call IZ interaction. But you can also have these ones in other systems that we also use it. And this is but you can also produce Hamiltonians like that, okay? You can simulate, you can do simulations, and from these you can produce things like that. It is easily done. Although some experiments took longer than others. Alexander showed you some experiments yesterday that took about 2 months to be performed continuously. And of course, we have to stop and sometimes recalibrate the system and so on. But sometimes they took a long time to be performed. Okay, it's not and easily performed, and if you have only a few measurements to be done. If you have lots of measurements to be done, they can take weeks or months to be performed. So we have these the Zim interaction, and you can easily manipulate the population between the states and also the coherence of the states. Okay. And so this Hamiltonian, we call these radio frequency pulses, okay, because they are in the range of microwaves, not microwaves, radio frequencies, and it's about 500 megahertz, 125 megahertz, and we can apply these pulses. And if you when you do this, you are creating unitary transformations. So that's what we can do in our system. And and we can apply lots of these pulses, varying frequencies, varying amplitudes, and varying phase as well. This is if you put lots of spins, the things get more complicated. So you have this, in this work here, we were able, with a collaboration with CBPF and Waterloo, IQC, and Waterloo University, that we were able to control and perform operations in our 4-qubit systems. And we actually, Alexander showed you one yesterday, a sequence with lots of pulses. Where he could manipulate the amplitude and the phase of each pulses individually. And how did he find these operations? He used a computation method which is very costly. It's called grape algorithm. And if your operation is too complicated, you have to fit this about 200 parameters in order to get this the operation you want to perform. In this work, I did with a former student of mine, John Patterson, and we developed a way that a way to not fit 200 parameters, but reduce the number to 10 to 20 parameters. But modulating this is expanding the modulation amplitude and phase sine waves in fitting these parameters here: A, B, C, D, E, F, G. Not E, oh, sorry, D, E, F, G. Because it's you can expand any function in Fourier transform, so use sine. You can use any other function. You can use polynomial as well. But we thought this was better. And we didn't need money of this function. So these are 4 to 5 here, 4 to 5 here, and it creates these structures here. This is for example, in these systems is a 4-qubit system. The interactions between the spins are very strong. So when you flip one, when you try to flip one, you move in the others as well. So you have to do things to compensate it. So for example, if you want to I saw you, okay. And if you want to implement these things, it's very hard, okay? Different from the 2-qubit system. So, for example, if you want to go from the state 0, 0, 0 to the state 0, 0, 0, 1, you have to compensate while you're flipping that 1 qubit. You have to compensate for the evolution of all the others. So. Using these, we did some nice work, which was never published. I'm sorry about that, but we can talk about that later. And that's we could implement these things. These are 90-degree rotations along the x direction in the spin 1 and spin 1 and 2, 190 along the x direction in spin 1 and 2. And this is the modulation in the amplitude and modulation in the phase. It seems to be cut, but it's not. It's only because the phase can vary from 0 to 160. Okay. So this was the molecule. With 4 carbons. The experiments were performed in Waterloo. And with this method, we can achieve high fidelities that pulses. It's this is published. Okay. So we can perform things with more than 2 qubits here and elsewhere. It's not easy, but it's doable. More than 4 or qubits or there are other systems, but they are very harder to control. As the number of qubits increase in NMR, the harder to control them, and so the implementation doesn't. They have to be simpler. Okay. So this is forget this equation here. It's a mistake. But we have in our system we have a thermostat. Alexandre already did explain that to you. But since we were doing only performing unitary operations, and we only see the pure part of the density matrix. Okay, nothing on this part here, which is way larger, can be measured. It's this epsilon is 10 to minus 5, 10 to minus 6 sometimes. Depends on the applied magnetic field and the temperature. The more the coil that apply the strong magnetic field is cooled, but the sample is at room temperature. Okay, and so you only see in NMR all the spectra, all the measurements, all the signal that you measure come from this pure part here. So, and that's a typical NMR experiment. Okay, in these 2 qubits. Of course, these parameters varies with the sample. We want to dilute the system. For example, we cannot put a tube with chloroform and perform experiments because the interaction between them will be high, and this will mess up the experiment. So you dilute this 10 to minus 4, 10 to not 4, but 1%, more or less, or 0.1% of the samples. We dilute with something else, which also good for the experiment. So we can guarantee that the signals are coming from molecules that are not interacting with each other. So all the interactions we see are the interactions of the qubits with themselves inside that molecule, right? So there are the typical relaxation times where we take, which is the time that the system take to return to the equilibrium. For example, in the hydrogen, the spin is 7 seconds. In the carbons, 11 seconds. But also we have 2 relaxation times. This is when the system returns to the full equilibrium state. But the most important time are these ones here, T2. Okay, because this is the times that the system lose the coherence. After these times, you cannot use the system anymore. But We can do many operations, not infinity, during this time. For example, as Alexandre showed you yesterday, while implementing a quantum engine, we can do some cycles, 1, 2, maybe 3, with no loss, more or less. Not many of those. Okay. And this is a typical time of our experiments, the system. So Alexandre only left me one topic to cover. And this is the Quantum Axis demo, which is performed in 2016. The collaboration of the University of ABC in Brazil, Federal University of ABC in Brazil. ABC is 3 different cities, Santo André, São Bernardo, and São Caetano. So it's they don't like this name. They think it's ridiculous because it's a new university and relatively new university, and it was created to englobe these 3 cities in the middle of São Paulo. So we did this experiment here, which is we start from the equilibrium of this qubit equilibrium and drive an unitary operation very fast. So the the system doesn't have time to follow the unitary transformation, and this induces error in the system, irreversibility. And then we did a measurement. We use a second qubit as a memory. We perform a measurement like it was the DEMOS memory. If you all remember, I should put another figure here now. Now I see. If you all remember, the Maxwell's Demon paradox was solved when Charles Bennett, had the insight that the DEMOS memory had to be included in the thermal cycle, right? So, and the information in the DEMOS memory had to be erased in order to eliminate the paradox. And so that we implemented here with this demo. It's a nice figure. It's made from Roberto Serra, works at UFABC. And he performs a measurement. And then we use this information here to apply a feedback operation that in this we can reduce the irreversibility effect on the system. Okay? So this is the, okay, we start with 2 qubits here. This is equilibrium. The other one, it's at the 0 state. And we drive the equilibrium system through a unitary operation. I should explain which one it was this, but I think this was a radio frequency pulse applied on the x direction. I have to check the paper to see. And this box here, blue box, it's almost invisible, is the measurement of the system and keeping the information on the DEMOS memory. There's a pulse gradient here. And this here is a trick that we disturb the system with a small rotation just to see how efficient was this feedback control. And how the information could be recovered. And this is the quantum, not quantum states, quantum tomography process of the system. It agrees with the very nicely with the theoretical predictions. And is the error that we introduce here with the applying disturbing the system is and a little more to try to see how much of the information we could recover applying this feedback. Okay. And these are the main results, the production entropy. As we do this for various several temperatures, and how with the disturbing the system with that small rotations. Of course, if you disturb it too much, you lose all the information. And the points, the colorful points are the experimental data, and you can see error bars there, and the lines are theoretical predictions. In this paper here, there is also theoretical result with this equation here, what was calculated for this feedback system by Patrice Camatti and Roberto Serra. Okay, and this is the main result of this paper. Okay. And I'll talk a little more about this because I have time. And because I think Alexandre did it very quickly yesterday. He want to show more things, and but this is the work that we did some. What we did here is to create two thermostates at two different temperatures, not very different, but one is cold, one is hot. We call this one. So we use the 2 qubits again. And the decimatrix is like this. But they could also have this part here, which creates a correlation between the two systems. But this correlation, it's in a way that if you trace the matrix, the whole matrix, you see the system in the equilibrium state. This one. This is all experimental, okay? I'm showing all the experiments for you. So there's the whole density matrix. They don't. We're not showing here the complex part, but they are neglectable. And so if you trace here, you see the system A in a given temperature, and the system B in a given temperature. By temperature, I mean spin temperature. It's not a new thing. It's a thing that's been around for decades. It's very common in nuclear magnetic resonance. We can produce. Since there's only two energy levels, you can produce a Boltzmann distribution there. It's very easy. Okay? And that's what we did. And so this one here should be the state preparation. And this one here should be the interaction, which I'm going to talk later. No, I think all this is state preparation. So you can see it takes a long process to create this state. I remember that it was this we can do easily. Sorry, this we can do easily, but the other one was it took us some time to obtain that particular distributions and a nice state with small correlations, things like that. But this one, okay. And after doing that, we let the system interact. It means that the qubits interact with each other through this Hamiltonian here. This Alionziski, Moria, Hamiltonian, I don't know how to pronounce that. And during a certain period of time. So what happened here is that this is spin A and spin B. So spin A is a little hotter than spin B. See, 1.2, 1.0. And if you're not correlated, the spin with the interaction, they in contact, they will reach a thermal equilibrium. So spin A will decrease temperature and spin B will increase temperature. However, if they are correlated, spin A will become hotter and spin B will become colder, all right? And of course, if I continue the interaction, then since it's a unitary operation, the system will come back to the way it was before. It's not perfect, but it is acceptable. Okay. And what's happening here is that what the system is consumed that correlation to do this thing that we should say it's impossible, right? So it's analogous of the Demon's memory, all right? You use information. You can use information to produce work, right? And here, what we're doing, you are consuming information. It's a form of correlations between the two systems to induce the thermal exchange in the other direction. So the system becomes uncorrelated. The hot goes to hotter, the cold goes to colder, but they are becoming uncorrelated. Okay. And this is a summary of what is happening. We have correlations. It's a nice figure I should put in somewhere. And TBPF now, this is a new lab. It was created and started function during the pandemic. We haven't done many things with that yet. It was installed in an inappropriate place here at BPF, and we have to reinstall it. And I'm nice to say that we have a nice collaboration with Sergio Muniz, who's over there, who is from USP. USP ou UFSCar? Sempre confundo. USP. USP São Carlos. They have two universities in the same city. It's very confusing. And so we're doing start doing some nice things with it. And Sergio has been collaborating with us. And he'll be happy to show you this lab. This lab is still being constructed right now and lots of equipment to be mounted. Since it's a quantum thermodynamics conference, we didn't say anything, but we're planning and we know how to do already. We did, there are some paper published, students being formed right at the moment, but we are constructing superconducting qubits here, okay? And so we have small chips being produced, and but part of the work is done here, and the other part is done in São Paulo at the same at São Carlos as well, and we have a big lab now to do everything in one place, both here and at São Carlos, and right now we have lots of equipments in boxes and they are not installed yet, but it will be finished, I hope, by the end of 2025. So interest in work with us, please contact Ivan, Alexandre, or me, or Sérgio. And thank you.
Thank you, Roberto. We have time for questions. Yes.
Thank you for the talk. Very interesting experiments, lots of them. I was curious about, you presented some results for a different molecule, a system in which there were 4 qubits in your molecule. I was curious about, and you show some fidelities, but you didn't say what type of, or at least I didn't understand, what type of operations were performed. So fidelity against what? If you could comment on that, please.
This operation here, okay? 90-degree pulses. For example, this pulse create in the first qubit, 180-degree pulses in the qubits 1 and 2, 90-degree pulses in the qubit 2, 180-degree pulse on the qubit 2 and 3, and qubit 3.
So these were both single qubit and 2 qubit operations?
Yes.
Okay, so you were really able to drive the whole 4 qubits
yes, independently.
Okay.
It's so it means that it rotate, for example, the last one, the green one, is rotate the third qubit 45 degrees while maintaining the other ones, the quantum state of the other ones.
Thank you very much.
Is it possible to perform conditional operations on the entangled system? So yes, so I measure part of the system, and according to the measurement setting, so I can do some type of entanglement or steering or no locality protocols.
I would say yes. Okay. But we can talk about it.
Yeah, I want to propose something.
Yeah, thank you. But I think it's possible. It doesn't matter if you start to see with a system that's entanglement, you can put some driver there, and I think it will go where you. Actually did this with scientific initiation students at some long time ago.
Okay.
Coffee.
Okay, yeah. So if we don't have more questions, so let's thank Roberto again.
You.
Alô? Tudo bem? Ok. Ah,
Ok. Oh, yes. Para baixo e para cima, para frente. E o de
sim,
cima
pra
é o
baixo.
pointer.
Ops.
É o de baixo. Isso. Okay, so now we can move to the next talk by Emmanuel, one-way street for the energy current, and ubiquitous phenomenon in boundary-driven asymmetric quantum spin chains. Thank you.
Okay, thank you for the chance to talk here. And well, the title is too long, but I will explain to you. That is a very interesting phenomenon in my opinion. Okay, thanks. It's a very simple but very interesting phenomenon in my opinion, and it happens for quantum spin chains. That is, well, for it's stronger than rectification, for example. That is when you are studying the heat flow or the energy flow in a chain. The usual you have two baths, and then we have the flow going from one bath to the other bath. And when you invert the bath or invert the chain, so we'll have the usual, in the usual case, we will have the inverted bath, the inverted flux. But rectification, for example, this phenomenon is stronger than rectification. When we invert the system, we have the inverted flux, but we'll have a larger flux in one of the directions. So we have a preferable way for the flow. That is the rectification. In our case, the one-way street phenomenon is the following. We have the chain and we have the baths, and then we see an energy flow going from one bath to another bath. Then we change the bath, but we keep the same current from in the same direction and the same magnitude. You know, there is no inversion of the energy current, and it happens for several spin quantum chains, as I show you. Okay, that's my collaborator Humberto Lemos, who is here, and Débora Oliveira, who is in IMPA, and Alberto de Paulo, who is in Minas Gerais, too. Okay, when we are talking about non-equilibrium statistical physics, we always think about transport, of course, because you know, transport is everywhere in open system. And we have the interesting fact is that after so many studies, we still have many open problems. For example, for a classical system, the Fourier law is a phenomenological law that states that the heat flux is proportional to the gradient of temperature. It has been proposed in 1822 by Fourier, but up to now we don't know the necessary and sufficient conditions for the occurrence of the Fourier law. And in the quantum scenarios, we have many other questions related to the properties of the transport, for example, diffusion, rectification, and so on. And so the situation is very difficult. And to study this, a good strategy is to take simple models and to investigate in detail these simple models, and then in order to get general results. And that's what we do. We take the XXZ model, that's the Hamiltonian is well known. We have this B term here, but later for the one-way street phenomenon, we need to take B equal to 0. That is, the phenomenon happens in the absence of external magnetic field. And okay, we'll take this XXZ model, and for the dynamics, we use the Lindblad master equation for the dynamics given by this expression here, where for the dissipator, in our first example, the dissipate will give by the limit for this Lindblad expression here, and for the sigma z polarization, that is, we have in the dissipate this operator sigma plus and sigma minus, that they are the creation and annihilation usual operators, and so you'll get the polarization for the BEF, FL and FR. Okay, and then we may study this, and it's easy to see that we have a continuity equation for the flow, for example, for the flow of magnetization. But we are interested in the energy, so we can write the energy as the sum of this epsilon here, and this epsilon is given by small 8, and this b is related to the external field, so you can forget this. But this 8 is related to the interaction between sides. And for the xxz, it's important to say that, of course, the phenomenon will happen only in asymmetric systems. So we get this, we introduce this delta J here change in N bond in order to get a symmetrical system. Okay, so we can derive as, again, a continuity equation for the derivation of the energy, of the average energy in the system, where this F here is given by this Fxx plus another term related to B, but okay, forget this B term. This Fxxz involve three sigma, that's the Pauli matrix, this 3 sigma matrix in different sites and different matrix too. See, we have sigma y, sigma z, and sigma x in any of the terms here. So to carry out our study, that is what we are trying to do. That's we are trying to study the system, what happens to the system when we invert the BEFs. So we'll take now F equal to FL, that is the polarization of the left BEF, and we'll take the polarization of the right BEF minus F. So the inverse of the BEFs, that is the change of FL by FR, is given by the change of the sign of F. And as I have said, we also consider B equal to 0. So let us try to find an operation that inverts the BEFs. So we take this U operator here, that is the product of sigma x. And of course, the adjunct of U is U to minus 1, because you know this matrix, the adjoint of sigma x is sigma x, and the inverse of sigma x is sigma x2. So in fact, U is equal to U minus 1 for our choice here. And so let us study the transformation of the matrix after this operations, this U operation. That is, we'll have where is it? Of course, it's given the Lindblad, the Lindblad expression ρ is related to the commutator of ρ and 8 plus a dissipator. And so the derivation of U minus 1 whole U is given by this expression here, that is the transformation of ρ times the transformation of 8 minus the transformation of 8 times the transformation of ρ plus the transformation of the dissipator. And well, what has it? Okay. it's possible to see that the transformation of 8 is 8 itself, because what is 8? 8 is given by the product of sigma x, and sigma y, and sigma z. So when we use this U, that is the product of one term by sigma x and sigma x again, u minus 1 is sigma x, and u is sigma x. So the terms in the Hamiltonian, the sigma x terms will stay being sigma x, of course, but the sigma y will become minus sigma y, but we have the product of 2 sigma y, and the same happens for sigma z. So 8 doesn't change with the transformation. And when you apply the transformation to the dissipator, it's easy to see that the dissipator becomes the dissipator of F becomes the dissipator of minus F. Why is that? See, that is the dissipator is given in terms of the product of this L operator here, and the L operator is given in terms of sigma plus and sigma minus, and F plus F and minus F. And when we apply the transformation, sigma plus go to sigma minus, and so the sign of F change here. So it's the same thing to transform the dissipator is the same as to change the sign of F. And so that is our conclusion is that if ρ is a solution of the Lindblad master equation with the given baths, then U minus 1 whole U is a solution of the Lindblad master equation with F changed by minus F, that is a solution of the system with inverted baths. Okay? So that is recalling the uniqueness of the non-equilibrium steady states of this Lindblad master equation. We can say this, that is, if ρ is the steady solution of the Lindblad master equation, then U minus 1 whole U is the steady solution of the Lindblad master equation with minus F. That is a solution of the system with inverted baths. So, oops, and so let us think about the heat current. We can say that the product here of the operator U minus 1 times the operator that defines the heat current times U, it will give the same, because this product is given in terms of 3 sigma matrices, and sigma y, sigma x, and sigma z. Sigma x becomes sigma x, sigma y becomes minus sigma y after the operation, and sigma z becomes minus sigma z. So the product of 2 minus given plus, and then it keeps the energy current. That is, when we study the average then of the energy current, we have the average is equal to the trace of ρ times F. That is, as I have said, this F doesn't change with the operation. Then we can introduce the operation here, and finally we conclude that is the trace of the transformation of ρ times F. That is the transformation of ρ is ρ of minus F. That is the conclusion. If F is the current, the energy current for the system with F is equal to the heat current of the system with minus F, that is for the system with inverted baths. And then we have the phenomenon there. Or if in fact we have the phenomenon for the, not for the homogeneous chains, because in the homogeneous chains, when we are studying it, if you have a flow from one bath to another bath, of course, when we invert the the chain, nothing happens because the chain is homogeneous, and then there is no sense that is the current will be determined by the BEFs, and then we should invert the current. So we may conclude them, that is, if you don't invert the current, we may conclude that the current is zero. But for a graded chain, that is for a chain with asymmetrical interactions, then we have this phenomenon, the one-way street phenomenon. That is, the heat, the energy flow will be determined by the asymmetry of the current one. Okay. Well, I have said one simple case, that is a system with sigma Z polarization at the boundaries. So it happens for many more complicated systems. For example, for this system here, when you take the dissipator, see these complicated dissipators here, W for the left dissipator and this V operators for the right dissipator. W is given by sigma 1Z plus I sigma 1X. That is, we have a sigma Y polarization here. And V, we have a sigma X polarization. See, it's given by sigma Y plus I sigma Z. And so, but even in this case, it's possible to find a transformation that leaves the BEF W to the BEF V and C. With this sigma R transformation here, that's strange, and sigma R minus 1 is this. It follows that the transformation of sigma X is sigma Y, and the transformation of sigma Y is sigma X. The transformation of sigma Z is minus sigma Z. Then, when we apply this transformation to the Lindblad master equation, we may see that the dissipator on the left side are transformed in the dissipator of the right side, and vice versa. That is, the dissipator of the right side are transforming the dissipator of the left side. So we are inverting the BEFs. And so, following the same strategy that I have said, it's possible to after showing that the transformation does not change the expression for the energy, so it's possible to see that the average of the energy current is the same of the average of the energy current with inverted BEFs. And so we still have here the one-way street phenomenon. Okay. Yeah, that is all. I have some reference here. Okay, thank you.
Thank you, Manuel. Questions?
Thank you for your talk. So you have this asymmetric term in the ZZ part of your Hamiltonian.
Yeah.
Does it have to have a specific shape, or is generic for any delta?
It's generic. There is no. We can change as we want. For example, a graded distribution.
Okay, but it has to be.
But we have carried out numerical computations because we have shown that we keep the current, but if the current is zero, then we keep the direction and the magnitude of the current. We show that we have a non-zero current for the asymmetrical chain.
Okay, and but it's in your results the form of the dissipator is very important. Correct?
Yeah. But we have shown this phenomenon for several dissipators, several dissipators. It's interesting. We always can find a transformation of left dissipator to the right dissipator. For example, for here, we have this not usual matrix here that takes the left dissipator to the right dissipator and the right dissipator to the left dissipator. So it changed the best.
Thank you.
Okay, thank you.
Okay, so that means, so your theorem says that one qubit will never, you can never have rectification, right? Because it's homogeneous.
Yeah, just one
So
qubit.
the minimum is 2 qubits.
Yeah, but yeah, I'm interested in the chains, so several qubits. Okay. Yeah.
And then my other question was, okay, and if you have like a more complex topology, like 2D topology, would this apply as well?
Well, I hope so, but I did not.
Because you have
the,
I mean, it's based on the continuity equation,
yeah,
symmetries, and
yeah,
so on.
yeah.
So
yeah, I hope so, but you know, it's necessary to carry out the computation. But I hope.
Yeah.
Yeah.
Okay. Thank you.
Okay. Thank you.
Hi, thank you for the nice talk. So I'm also a kind of follow-up of that of previous questions. So regarding the dissipator, it's the form is very important. So will this result still apply if you consider stronger internal couplings between these qubits? Because then this dissipator will probably not be valid. You have to go to these global master equations.
No, yeah, in this case, it's valid only for the boundary-driven system.
Ah, okay.
Yeah, not for for the other case. I don't have any idea. Yeah.
Thanks.
Okay, thank you.
So I don't really understand what physically makes the direction to be preferred. Like, it's not really from heat,
we
hot
have
to cold, right?
asymmetry in the chain.
Uh-huh.
So the asymmetry in the chain determines the direction of the flow.
And you don't even have to to worry where to put the hot or cold bath.
Yeah, no, because we have, I'm talking about the energy flow. We have heat and work here. So we don't have any thermodynamic problem because, yeah, we have heat and work and together. We can use the protocol of repeated interaction. Do you know the protocol? And we deduce the heat and the work and show that we don't have problem. But yeah, you know, it's strange.
Yeah. Do you have some intuition to it, maybe?
No, I don't have.
No. Okay. Thanks.
Okay, thank you.
Okay. So let's thank again for Emmanuel.
Okay, thank you.
And we have the coffee break now waiting for us. Hello, Mauro. Good morning.
Hello.
Afternoon.
Hi.
Hi. So, Mauro, can we try to share your slide presentation?
Can you hear me all right? Just to check. Yeah.
Yes, we can hear.
Okay, so I'm going to share my screen. Okay. Can you see my screen?
Yes, but it's not in the presentation mode. Perhaps if you okay.
It should be now. Yeah.
No, yeah, now it's in good shape. Okay, so we're back to our second session of the day. Unfortunately, Mauro are not here presentially, but at least he will present remotely his works. Mauro is going to discuss about non-equilibrium thermodynamics of quantum collapse models. And thank you. The word is yours, Mauro.
Well, it's me to thank you all for arranging the talk to be given online, and I'm very sorry for missing the opportunity to see friends that I don't see since a long time. So I'm very sorry and I apologize, but yeah. It is what it is, and this is going to be a discussion on a topic that would be partially covered by the work that Giorgio Zicari, for instance, will be presenting, and that I think, say, looking at the program, has not been covered before, which is the phenomenology of so-called quantum collapse models. And there is say a subtitle, which I think works more like a caveat and a recommendation than anything else, that if you don't want a headache, you should not work on collapse models. And I hope to convince you of that by the end of the presentation. So let me give credit to people that have contributed quite significantly to the various results, the achievement of the various results that I will be presenting. So one is Simone Artini, so PhD student in the group in Palermo that I've recently joined. Gabriele Lo Monaco is a researcher again at the Quantum Group in Palermo, and Sandro Donadi, who is in a superposition between Trieste and Belfast, and who is an expert, a world-class expert when the coherence effect ascribed to exotic collapse models are concerned. So most of the results that I will be presenting stem from the work done with Simone and then more recently jointly with Gabriele and Sandro. What is the plan? Okay, so what are we going to cover in the time? I'm not sure that I will cover the full 40 minutes that I have, but the time that I have, it depends on how long I talk. So I will first look into form and formalism of quantum collapse models. Okay, so we will look into how to make sense of these modelization for the collapse of the wave function. And we will then look into two of such models which have a name and a surname. Okay, so the so-called continuous spontaneous localization model, or CSL model, and that will be the topic of the talk given by Giorgio. I don't remember if later on or tomorrow. I think it's tomorrow. And then the Dioggi-Penrose model, which accounts for gravitational effects on the phenomenology of the coherent dynamics of quantum mechanical systems. But we will do it in a way that is slightly different from what you would find typically in literature addressing collapse models. We will do it through an explicitly out of equilibrium quantum thermodynamical approach. Why? Because as we are going to see, there will be a lot to learn from that sort of take, that sort of methodological route. And when your aim and your goal is to understand these models in some more detail. And the third part will be addressing a an extension of both the CSL and the Auger-Penrose model to so-called dissipative versions of them. And that will be, say, somehow an attempt at making sense and salvage some of the physical conclusions that you would expect from a reasonable model for describing the quantum to classical transition. Okay, so enough with the appetizers, and let's have a look at the forms and formalisms for the description of these models. And we do it by starting from the motivations for why people have been interested in formulating quantum collapse models. And the main motivation is the dichotomy between micro and macro. No? So a fair statement to make is that quantum effects are certified, certainly, through tons of quantum experiments, but that certification comes only from our best quantum labs. And of course, I mean, Ivan is leading one of them in Rio, and I still remember with joy the interactions with Ivan and his team. So hi, Ivan. But with the moment I move out from the somehow the ivory tower, the protected environment of our quantum labs, then it doesn't look like macroscopic quantum effects are that easy to achieve or to witness. And the big elephant in the room is basically, yeah, I mean, we don't see the Schrödinger cat at macro scale. And the big elephant in the room is why we don't do that. Okay, so what is wrong with witnessing macroscopic quantum effects? And the most accredited answer is the quantum to classical transition. So somehow, somewhere, at some point in the evolution of a quantum mechanical system that grows in scale, something happens that leads them towards mundane classical descriptions. And a series of questions stem from this observation. The first being, which is the fundamental mechanism, or which are the fundamental mechanisms that drive the quantum to classical transition. And linked to that is the question of whether any intrinsic limitation to the validity of quantum mechanics exists. So is there a scale in the size or degree of complexity of a system that beyond which we shouldn't really take or expect any quantum mechanical behavior? Is quantum mechanical description, say, valid at any large scale, or is it preposterous to investigate these sort of questions? And finally, and I will touch very briefly on that. Can we test whether or not all these questions make sense? Can we test whether or not there is an underlying fundamental mechanism responsible for the quantum to classical transition? And if there is a threshold, a clearly identifiable threshold in size, complexity of a given quantum system and dynamics, beyond which quantum theory becomes irrelevant. So we take issue from a giant, okay? From John Bell, stating that collapses occur more or less all the time, more or less everywhere. And by far and large, and needless to say, Bell didn't refer to the collapse of buildings, but to the collapse of wave functions. So when the attempt at describing the quantum to classical transition is at stake, well, Bell was a skeptical. Okay, so the typical explanation and description of the occurrence of the transition from quantum to classical makes use of a diagram similar to the stupid one that or reasons similar to the stupid diagram that I'm going to illustrate here, where I have on the vertical axis quantumness, and I'm deliberately say, being vague and very, how to say, airy-fairy on what quantumness means. It might be quantum correlations, it might be quantum coherence, or any indicator of quantum mechanical behavior that your experiment, your dynamics might suggest. On the horizontal axis, instead, there is complexity, and still I'm being deliberately vague. Okay, complexity might mean many things, from the size of your system to the mass of it for people interested in macroscopic quantum effects, the number of particles that take part to a given dynamics. And the observation, the empirical observation that we are dealing with every day is in experiments is that the larger the degree of complexity of your system, the more complicated it is to either see quantum mechanical effects in them or maintain any quantum mechanical feature in a complex system, in a complex quantum system. And say the typical view is that you say the environment is the Zureckian approach, the orthodox approach, which is that the environment monitors your quantum mechanical system. And by doing that, there is a pouring of information from your system to the environment that is lost. Such mechanism is responsible for the quantum to classical transition. The interpretation is very appealing, is sexy, certainly so. But still leaves a few points open and unaddressed. The most relevant one is that this interpretation doesn't clarify the mechanism behind the occurrence of the quantum to classical transition. And wherever there is orthodoxy, there is also heterodoxy, and some rebels that think differently. And in this context, one of them was this guy, Giancarlo Ghirardi, so he spent most of his time in Trieste, at the University of Trieste, and Ghirardi was one of the main advocates, if not the pioneer, of an alternative interpretation of the way quantum mechanical effects are lost. And this heterodox approach to the quantum to classical transition stems from the request, or in a sense, the enforcement of a change in the way we describe the dynamics of a quantum mechanical system. So in Ghirardi's attempt at describing the way a quantum system loses its special quantum features, the Schrödinger equation, as we know it, it's only an approximation of the actual dynamics of any quantum system, both open and closed. What Ghirardi claimed for, together with other people working on the same topic, I mean, the most prominent one were Rimini and Weber, did some work either independently or together with Ghirardi, trying to elaborate on the idea that the Schrödinger equation needs to be modified so as to include ab initio, so to say, a physical mechanism that is responsible explicitly for wave packet reduction. So in Ghirardi's and co viewpoint, the Schrödinger equation, as we know it, the linear Schrödinger equation that we solve every day, it's just wrong. And they should then count and compass in it a nonlinear mechanism that, if properly crafted, and that's the controversial part, will account for the collapse of the wave function. Okay, how should I craft that term? That was never particularly well argued for. There were attempts by Ghirardi, Rimini, and Weber, by others as well, say a few years after the original proposal by Ghirardi. But it boils down, everything seems to boil down to a single very reasonable request made by Gilson a few years later, who basically said that the form of the modification to the Schrödinger equation is basically unambiguously identified by requesting the condition for no faster than light dynamics and evolution. So basically consistency with relativity will enforce in a non-ambiguous manner the modifications, the addition that you will have to make to the Schrödinger equation to make it, so to say, embedding explicitly a collapse mechanism. The consequence of somehow the mixture of take from Ghirardi and the request from Gilson is that in this new formalization and modeling of quantum dynamics, density matrices will evolve linearly, because that's what we see. I mean, we witness ensemble averages and dynamics of ensemble averages unless you really look into trajectories of your system. And while Schrödinger, say, wave functions and the state vector can evolve non-linearly, even more, they will evolve stochastically. Okay, and then there is, say, even bigger claim. Not only the density matrices will evolve linearly, but in the framework, a la Ghirardi, Rimini, Webb, and Gilson, the dynamics will be fully Markovian, fully memoryless. And so, I mean, these two questions will encompass basically these two features. On one hand, you will have a Markovian Lindblad-like master equation with suitable jump operators that describe the mechanism responsible for the reduction of your wave packet. On the other hand, you will have, a stochastic and nonlinear Schrödinger equation that will be really a rather complicated business to account for. Okay, so the Schrödinger equation for the state vector will account for a Wiener process, accounting for stochasticity, will have explicitly an observable of the system that is affected by the mechanism, the collapse mechanism responsible for the loss of quantum features, and typically the choice that people make is that of having position as the observable that is affected by the fundamental collapse mechanism, which I stress it, occurs even if your system is closed. So it doesn't, you don't need, in this framework, you don't need to claim, you don't need to invoke any environment. Your collapse would occur even if your system is perfectly unitarily evolving. The only difference would be that if your system is quantum mechanical, is microscopic in nature, then in size, in the degree of complexity, so to say, then the rate at which the spontaneous collapse would occur will be very, very low. So you will have to wait a very long time before you would see a spontaneous collapse of the wave function, while the rate at which the spontaneous collapse will take place is scales very fastly with the complexity of your system. So macroscopic systems or mesoscopic systems will collapse much more frequently than what microscopic ones will make. Okay, lambda here is the coupling to this sort of noise field that is there, whether or not your system is open or not, and that is responsible precisely for the collapse mechanism. But Ghirardi, Webb, and Rimini never investigated or dug into the reasons, the motivations for the collapse to take place. So basically, what is the underlying mechanism responsible for the spontaneous collapse? While Georgi Penrose put their finger precisely on that, claiming that whenever I have a superposition, a spatial superposition of a quantum mechanical system, then the state of this system, due to the modification of space-time that a spatial superposition would imply and entail, will result in an unstable state. An unstable state that will collapse at a rate that will be basically dictated by gravitational mechanism. So in the Georgi-Penrose explanation for spontaneous collapse, the rate at which my quantum mechanical system will lose quantum feature will be dictated entirely by basically classical gravitational features. And together with such a collapse, there will be a diffusion process, okay, associated with it. Beautiful formulation. Again, going back to a little bit of formalism, the sort of dynamics at the Schrödinger, at the Schrödinger nonlinear and stochastic Schrödinger equation level that we should be able to track looks a little bit like this messy two-line equation here, where the nonlinear term, so the stochastic term is the one proportional to the linear increment, while there is a term directly linked to the mass density of my system. So I'm literally taking the pictures, Diogene and Penrose, and this mass density term will account basically for what is happening to my system at two different points in space and at a given time. And then if I make some reasonable claims, like the following, like assuming that my mechanism for spontaneous collapse will have some form of characteristic length that here I call RC, and that the dynamics of my system of interest occurs well within such characteristic length, such correlation length for my environment, then I can make some approximation to my dynamics that leads to my master equation that leads me directly to an explicit form for the jump operators that account for the non-unitary evolution of my system. Okay, so the Lindblad term, the Tentes, the master equation takes the form that you see at the bottom of this slide, where the gamma function is basically a rate, an effective rate at which the effect of the not the collapse mechanism. I was tempted to say the environment, and there is no environment at this stage in this formalism, but the effect of the collapse mechanism will take place. So gamma is somehow a point of notice, so something that we should focus our attention on. So given that I have explicitly addressed continuous spontaneous localization, so Ghirardi-Rimini-Weber, and the Diogene-Penrose formulation of these spontaneous collapse models, let's have a look at what this gamma function looks like in the two formulations. Okay, and by doing calculations and say the group of Angelo Bassi did basically most of the literature available on the field, well, you can gather some explicit forms in under reasonable dynamical assumptions for the expression of these rates. So in the continuous spontaneous localization in the CSL picture, the gamma ray depends basically on two parameters: a proper strength of the coherence mechanism, that is small gamma, and RC, which I explained before, and that's this characteristic length for my collapse to take place. So the field that is somehow responsible for the collapse as a correlation length that is RC. And in this equation, M0 is the mass of a single nucleon of my piece of matter. While in the Diogene-Penrose formulation, there is only, there is basically, beside big G, I said the mechanism is intrinsically gravitational. There is only one parameter that needs to be considered, and that's R0. These are not here. So what is that? This is some form of a cutoff that I need to introduce to my model, because otherwise the spontaneous collapse induced by gravity will be basically instantaneous. And that cannot be the case, right? Because of experimental evidence. So Diogene and Penrose separately elaborated their own formulation of the gravity-induced mechanism for spontaneous collapse, introducing this sort of cutoff, phenomenological cutoff, that will get rid of the instantaneous nature of the mechanism of the collapse. Now, underlying the two formulations is basically the very same mathematics. So you can take the two collapse mechanisms and condense them in a unifying picture. So basically the very same equations, but with different rates. So you can map one model into the other and address both at the same time. And so far, the study of these models has taken quite a bit of attention from the experimental community as well. And the idea is that of trying and rule them out. Okay, so not many people believe in the tenability of these models or in the effectiveness of the description of the quantum to classical transition. So the attempt at the experimental level is that to understand, first of all, in which parameter range they are credible, they are tenable, and second, whether or not we have an ultimate experimental platform that will undeniably, unambiguously put the nail in the coffin of collapse models. So the outcomes of experiments that are currently being done in this framework is basically embodied by the so-called exclusion plots, which look a little bit like this one. Okay, so on the left-hand side, you have what people have produced for the continuous spontaneous localization model. On the right-hand side, you have a simpler one for the Dioggi-Penrose, and these colored regions are basically regions of parameter space in both models that have been excluded by current experiments. Okay, I don't go into the details of which experiment is which, so which color addresses which experiments. But for instance, for the case of continuous spontaneous localization, we have excluded most of the range of parameters that people believe would be credible or say reasonable for the model itself, and we have only this rectangular white colored region at the center of the exclusion plot that we will have to investigate. Still, it's nearly 4 orders of magnitude on the horizontal axis and some 6 orders of magnitude on the vertical side to exclude. Okay, so there is quite a lot of work that needs to be done in order to be able to say, well, continuous spontaneous localization cannot take place. While as far as R0 is considered in the Dioggi-Penrose model, a few experiments from observation taken by through the ELISA Pathfinder mission to X-ray emission gathered from the Gran Sasso experiments have excluded some range of values of the phenomenological parameter that enters into the model itself. Still, we have a few orders of magnitude to cover. And so job not done. The scope of the work that Simone and Gabriele and Sandro are doing is basically trying and putting nails on coffins from a different take, so from the take of non-equilibrium thermodynamics. And in order to do that, we took the dynamics, the unifying dynamics encompassed by, say, spontaneous collapse models, whether of the Dioggi-Penrose form of the CSL form, and translate that into equations in phase space that we can track. So in mind, what we have is the dynamics of an harmonic oscillator undergoing its own free dynamics and subjected to this fundamental mechanism for collapse. Why? The reason is that this is the experimental, this is the situation that is closest to the most advanced experimental platforms addressing these mechanisms these days. And that's the framework of levitated optomechanics or magnetomechanics. So basically mechanical systems that are suspended by either light-based mechanisms or magnetic mechanisms that are so well isolated from any conceivable source of noise that if I see any decoherence effect, the hope is that I will be able to ascribe it maybe entirely to a potential collapse mechanism. So what we did was taking issue from the dynamics of harmonic oscillators, freely evolving one, and look at them from phase-space picture. So what we did was deriving the Fokke-Planck equation for the Wigner function of associated with the state of an harmonic system undergoing a collapse. a collapse mechanism in the universal, in the, say, unifying feature framework that I have introduced before. And the equation that you get is something slightly, I mean, slightly exotic. Okay, so something that needs a little bit of attention. First of all, you have the unitary bit that is accounted for by a Moyal bracket. And then you have a diffusion term, this term with the Laplacian, so the double derivative with respect to momentum, that gives rise to diffusion in momentum direction. Okay, so what you should see in the video is basically the dynamics of the Wigner function in time. Time here is measured in Planck's units. You see that the diffusion takes place. And also, we started from an isotropic state, and then the diffusion terms occurs anisotropically, expanding the wave function, sorry, the Wigner function along in phase space. That's entirely, and the rotation that you can see is entirely due to the free evolution of my system, so the Moyal bracket part. The expansion, on the other hand, is due to the diffusion in momentum dictated by the collapse mechanism. And in order to feed thermodynamics in these dynamics, so we made use of the tools that Gabriel Landi with his group, and they were generous enough to involve me in the formulation of these tools. Came up with a few years ago. No, so basically measuring entropy through the Wigner function. So the Wigner entropy. Why? Because this quantity has some very nice thermodynamic interpretation in terms of a free energy difference. For Gaussian states is something very intuitive. It's linked basically to the purity of your system, of the state of your system, the Rene-2 entropy, and it makes sense from a thermodynamic viewpoint because, say, for instance, if I quantify entropy production for thermal state defined as the relative Wigner entropy between your instantaneous Wigner, say the Wigner function of your instantaneous state and the equilibrium state of your dynamics. Well, this quantity evaluated for thermal states makes sense from a thermodynamic viewpoint. Okay, so it goes back to what you would expect from the von Neumann entropy-based argument. So it's a good tool, especially if you're dealing with Gaussian systems as we are dealing now. Problem is that the moment I deal with entropy production rates in an harmonic, a quantum mechanical system described, a quantum harmonic oscillator affected by the continuous spontaneous localization mechanism, what I find out is that in time, the entropy production rate goes from positive values all the way down to negative ones, and quite large ones as well. So I basically break the second law. So these dynamics breaks the second law of thermodynamics. And if I look at the relative entropy between my state in time and what I would expect as the equilibrium state of my system, then I find that this relative entropy diverges. So my system has a minimum at some time that we can explain. So there is a time at which my system tries to be a thermal state at a given meaningful temperature that you would ascribe to some form of steady state, but then it deviates from it and it takes the form of a non-equilibrium steady state, which has some nice implications. It's a non-physical state at all. So basically, this analysis tells you that the long time description of your collapse, say your collapse mechanism, is untenable from a thermodynamic viewpoint. Then, if you wonder what happens for the Dioggi-Penrose model, well, you have the same sort of headache. No? So the entropy production rate at some point in time goes from positive to negative values, and again, quite large negative values, and showcasing a similar phenomenology on the relative entropy. So you don't get a thermal state. You don't get anything that looks like an equilibrium state at all. And you don't get anything that looks like a physical state in any form and nature. So the conclusion that you can reach is that these models are thermodynamically inconsistent. And the only place where they should be is maybe the bin. So people are basically wasting their own time looking at models that, although nice in trying to explain pen and paper, the phenomenology of the quantum to classical transition should be not be considered, should not be accounted for, because they are thermodynamically inconsistent. They simply don't hold. And if that's the conclusion, then my talk will be done now, but I will still bother you for 5 more minutes, because just like some politicians that are very difficult to get rid of, you shouldn't be too fast in ruling them out, okay, ruling quantum collapse models out of the picture. And the reason why you shouldn't go too fast is that you can extend them, you can improve them, making them explicitly dissipative. What I mean by that is that you can extend, and this has been done in a number of work, again by the Bassi group a few years ago with Andreas Birne, and more recently Laos Diogi with Matteo Carlesso, again a member of the Trieste team, extended the Diogi-Penrose mechanism to dissipative formulation, where together with the diffusion mechanism that I have illustrated so far, there is also a friction term, a dissipative term, that enforces some form of effective temperature for the steady state, for the stationary state of your system. So you should be careful in attributing a meaning to this beta parameter in the new jump operators in these extended dissipative mechanisms, because and attribute the meaning of that temperature to the temperature of the noise mechanism itself. It's not. So one can estimate somehow the temper from energetic arguments, which is the temperature of the noise mechanism, that noise field that I've introduced in the case of the continuous spontaneous localization mechanism, and that temperature will not be the same as beta here, while that beta will be, again, the temperature of your steady state. So once more, you are going to achieve a non-equilibrium steady state at a temperature that is not that of the environment, but things look a little bit more meaningful. Why is that? Well, first of all, if you go into the phase space picture, your Fokker-Planck equation acquires an extra term here, which is entirely due to the friction-like mechanism that these dissipative extensions enforce to my model. As you can see, F, so the friction rate, depends entirely on this fictitious temperature that you're putting in. And if you and you can kill it the moment. So if you kill F, you are basically going back to the formulation of the continuous spontaneous localization model or the Diogi-Penrose model that we went through so far. And if you start looking once more at the thermodynamics of these models, then everything is nice and shiny, right? So entropy production rates remain positive, relative entropies don't explode. There is nothing such as a critical time at which your entropy production rate behaves, so to say, pathologically. And yet, I mean, these conclusions can be reached only under very, very special conditions. So your entropy production rate in the dissipative formulation of the continuous of the collapse models makes sense. So the thermodynamics of them will make sense only if you start from a restricted subset of initial state. So your dynamics doesn't look like anything very, very nice and very, say, credible if you start from certain classes of state that we are trying to characterize. It looks like you should start from isotropic states in phase space, moment you deviate from them, then you might have transient periods where your entropy production rate becomes negative. It goes back to a positive value later on, but there is a transient where things don't match, don't make sense at the thermodynamic level. I mean, you should take things positively, as the Monty Python said, and look at the bright side of life and collapse models, because even though your, say, modified, beefed up, dissipative version of spontaneous collapse still don't hold water entirely, there is a set of things that you can understand. For instance, you can understand up to when, in terms of the beta parameter, you can ensure that the collapse, say, the dissipative version of your collapse mechanism are tenable, are thermodynamically consistent, and therefore set bounds to this temperature of the steady state that you should aim at achieving. The meaning, the physical meaning of that is still, of that bound, is still quite obscure, at least as far as I'm concerned. So we are working on it, and there will be a paper coming up where all these things are nailed down in some quantitative terms, and certainly in a way that is much better than what I've been able to say in this 40 minutes. With that, I think I should conclude. These are the people that put the bread on the table of the two teams that suffer my tantrums, one in Belfast, one in Palermo. And with that, I thank you for your attention, and I thank the organizers for their patience with me. Thank you, Taisa. Thank you, Diogo. Thank you so much.
Thank you, Mauro. So we have time for questions.
Hi, can you hear me, Mauro?
Yes.
Okay, so as far as I understand, I mean, one of the advantages of the collapse model is that you don't have an external bath and all these things. So what do you gain if you have this collapse model with dissipative? Because then the system is open also. I mean, what is this kind of models, and what do we gain then?
Very good. Very good.
The usual decoherence.
That's a fantastic question. So the idea is that basically you can still, so to say, keep the picture that is kosher as far as the collapse models are concerned. So a picture where there is no environment, but you can attach a temperature to the field responsible, this sort of abstract mechanism that is responsible for your collapse, and that is there regardless of whether or not you have an environment affecting your system. So the dissipative version of collapse models basically enforce an effective temperature of the noise field that is responsible for the collapse, whether this is, say, dynamical collapse in the continuous spontaneous localization mechanism or gravitationally induced one. So whether that is a parameter that entails some quantum formulation of gravity or not, but that is the meaning of the dissipative mechanism, something that stems from an effective temperature of the environment with which you are interacting. Oh, sorry, of the field that you are with which you are interacting.
Oh, okay. Ciao, Mauro. Marcelo França, how are you doing? So actually, my question was in the same direction somehow as Thiago's. Is like, what would be the physical motivation behind this dissipative term? But I think it's more or less what you have already answered. So
thank you so much.
Okay. So I have a question concerning the first part, just to clarify. So when can you falsify these models? I mean, is the value of these couplings or parameters below which you can say okay, you do not
very
work?
good. So let me go to the exclusion plot. Okay. So hi Saru, by the way. So I think you are referring to this part, right? Right, Saro? Yeah.
Yes.
So the falsification basically tells you that the following. Take, for instance, in the left-hand side, so the plot on the left bottom corner. Okay, so the one for the CSL. Have a look at the I don't know, at the green colored regions, and there are various shades of green because there are various experiments. So such experiments have explored the range of parameters lambda and RC covered by the green shade. And what they did was gathering measurements, and what outcomes tell you within these within the operating conditions of my experiments, which would test or correspond to CSL mechanisms characterized by, say, the green shaded region of values for lambda and RC, I have not seen any collapse that I cannot account for by standard decoherence mechanism. So I didn't see any anomalous effect in the dissipative dynamics, in the decoherence dynamics of my system that I can ascribe to my collapses. There is a range of values, the white colored one, where we don't have currently an experiment that can address the tenability or not of the collapse mechanism, and that's, say, somehow annoying, given that there is an estimate of the given by Ghirardi, Rimini, and Weber, is that GRW point that you see in the plot. So GRW conjectured that the actual value of RC and lambda should be those in correspondence of that dot that falls slightly within the white colored region. So we cannot claim there is no collapse taking place in that region. And the main effort that people are trying to do right now at the experimental level is to come up with an experiment that is able to falsify these models precisely in that region.
So there is no way.
For the Diogene Penrose, apologies, I've cut you short, please.
No, but so just to understand, so there is no way in which I come up and say GRW should be even smaller in that diagram. So
there is no way to claim that it won't be such. Okay, so the gray area excludes some value, but I don't know anything about the white colored one. While the meaning of the diagram for the Diogene Penrose tells you that any are not between 10 to minus 16 and 10 to minus probably 12, something like that, should be excluded because there are X-ray based experiments in Catalina Curciano's say labs in Gran Sasso, where no collapse has been observed.
Okay, we have time for 2 more fast questions, perhaps.
Hi, Mauro. Boyuna here. I miss you.
Boyuna, hi.
Let me ask you something. The collapse postulate works for a generic operator. I choose to measure some operator and then the collapse happens. And why I can choose different operators in that collapse models you showed or in your treatment for them?
Okay, very good. So, Boyuna, I'm not sure that the answer will be satisfactory, but your question is also a question that I have and I had. And if I understand it correctly, it boils down to why I'm picking up position and not a generic operator, and shouldn't I explore a generic operator in my master equation for the description of the collapse. So in principle, I would say you're absolutely right. And every time I ask the experts, they tell me, which I'm not, by the way, they tell me, well, it's natural to pick up position because what you are interested in is basically cut states. So something being here and there at the same time into different locations. And collapse, if it takes place, we'll try to localize your system in space. So ultimately, what they claim is that the coupling to position is the most fundamental mechanism that you should come up with. So I have only partially satisfactory answer. It doesn't satisfy me fully. I can see the logic, but not the rigor behind that. So I agree with you, and I don't see any reason why we shouldn't look into arbitrary operators. Maybe this means that we will have headaches coming up from collapse models for a few more years.
Hi, Mauro. Since you mentioned John Bell, I was wondering what you would think of these models, and if possibly these mathematical tools you developed here could be used in other contexts, maybe.
Okay, beautiful question. So John Bell was a skeptical of the effect of the environmental mechanisms monitoring the state of a given quantum system. He spoke very bluntly and very famously of the shifty split, right? So basically the convenient capabilities that we have in the standard interpretation of the coherence of moving the point at which environment takes place, the environmental effect takes place, basically at your best convenience, not to your best convenience. So I'm not sure what you would think. What I know is that what we know is that he was skeptical of the orthodox take.
Can you violate no locality with collapse models?
Okay, yes, it's fully compatible with that. Yes, there is no problem with that. Angelo has beautiful papers on this.
Okay, so I think that we are on time. So let's thank again for Mauro.
Thank you so much. Thank you very much indeed.
Thank you for taking your time to make the presentation remotely.
Honor. Bye.
Okay, and the next speaker is Mario, right? Aqui. Perto da gola.
Oi? Alô? Sim. Agora tem. Eu acho que não vai passar, porque acho que eu tenho que clicar ali para passar. Ah, tá passando?
Para frente, para trás, e aqui é o
laser. Ah, ótimo. Onde é para frente?
O para frente é o do meio.
É do meio, sim.
Isso.
Ah, tá ótimo.
O de baixo é para trás.
Não, acho que estou perdendo o pé. Não, tem o de baixo.
É o de baixo aqui.
Ah, é o de baixo.
Isso, é.
Aqui 2 vezes vai para frente nisso?
É, não só uma vez, só vai para frente. O de baixo vai para trás.
Já foi.
E em cima é o point.
Ah, tá. Ih, saiu. Acho que foi eu que tirei. Não.
Pessoal. Aí, ó. Ele tá preparando.
Ah, ele que tá mexendo ou sou eu?
Não, é ele.
Ah, tá, percebe.
Só espera um pouquinho. Ok, cheque aí para o espaço.
Não.
Aí, agora cheque.
Não, é ele que tá passando, não sou eu.
Okay, so our next speaker is Mario Reis, talking about the quantum thermodynamics process based on the metal complexes. Okay. Não tá indo? Ah, sim. Esse aqui é para frente.
Ah, tá, ao contrário. Tá. Ao contrário.
Isso, é.
Ao contrário.
Okay, so the word is yours, Mario.
Well, good morning, everybody, and thanks for the organizers I know that in this conference, in this workshop, there are a lot of organizers here, and to give me this slot to present this work. And my background is not in quantum thermodynamics. I came from classical thermodynamics, working with producing materials for classical thermodynamics, producing thermal machines for classical thermodynamics, and I hope to contribute with these backgrounds of classical thermodynamics to this community. And the idea of this work is to try to introduce this idea of two potentials, isothermal adiabatic temperature change. Isothermal is, sorry, let me present here. Yeah, it's not, não tem. So the idea is trying to introduce the isothermal process, the isothermal entropy change, and the adiabatic process, the temperature adiabatic change. These two are potentials for these two processes that we are trying to use a methodology, a comparison of the classical process. You use this classical process to produce this idea from the classical process to deliver for this community these two potentials. Okay, and use these metal complexes that are several materials that we are very often using in our labs to try to verify these quantum potentials. Okay. The results that I present here are deposited in this article that people are interested. You can find here in this article, and also of course you can discuss if you are interested. Well, starting from the isothermal process, what's the main idea? I will start with a brief survey about the classical isothermal process, because our idea is to make a comparison between the classical process and the quantum process, and then to try to deliver the isothermal adiabatic, the isothermal entropy change. Okay, let's see here a lattice with spins. Okay, without magnetic fields. Okay, without working parameter. Okay, and here we have the same lattice with magnetic fields. Considering a simple first law of thermodynamics, we have the magnetic fields, work change, okay, and then we have the internal energy of the system, and then heat is released to the thermal reservoir. Considering the first law of thermodynamics, there are two ways to try to get these amounts of heat delivered to the thermal reservoir, because to try to make thermal machines, considering the classical and quantum cases, we need to get these amounts of heat delivered to the thermal reservoir. The first way is to consider the first law of thermodynamics. However, it's not easy to get the internal energy and the working parameter. The second way is to try to get to consider the second law of thermodynamics and to get this amount of heat considering the entropy. For this case here, we can consider the entropy with two contributions, the spin contribution and the lattice contribution, considering the classical case. The spin contribution, the lattice contribution. The spin contribution depends on the temperature and magnetic fields. The lattice contribution depends only on the temperature. Okay? When we make this, when we apply magnetic fields, the total entropy change will depend only on the spin, because this lattice contribution depends only on the temperature. Okay? So you see here in this simple proposal that the total entropy change, considering the second law of the thermodynamics, to try to get this amount of heat exchanged with the thermal reservoir. That's our goal to make a thermal machine, because our goal is to obtain the amount of heat exchanged with the thermal reservoir. Okay, so in this case here, considering these two contributions of entropy, we see that the total entropy change depends only on the spin contribution, because the lattice depends only on the temperature. Okay, let's see the spin contribution only. Considering this Maxwell relation, we see that the entropy, there is a relation with the entropy, magnetic fields, magnetization, and temperature. By integrating this equation, we see that this entropy change depends on the magnetic field, temperature, and magnetization. Okay? Can you click? Pode, por favor, clicar nesse ícone? Can you please click in this icon here? Okay. It's a classical picture, okay? I'm not talking about the quantum case for this moment. To make a classical refrigerator, the one we use in our home, for example, here is the if you remember from the previous equation, here is the magnetization as a function of magnetic fields for several values of temperature for a certain material, okay? For a certain material. From these measurements, we can obtain the isothermal entropy change. That's the amount of heat that the material exchanges with the reservoir, okay? As a function of temperature and magnetic fields. So classically, we can obtain, can you click out? Can you click out, please? Okay, so from the classical point of view, if you know the magnetization, temperature, and magnetic fields, it's possible to obtain the isothermal entropy change, and consequently the total entropy change, and consequently the amount of heat exchanged with the thermal reservoir. Okay, that's the classical case. If you know this, it's what we have done. If you know this, the idea was to make a parallel with these ideas to obtain this amount of heat exchanged with a thermal reservoir in the quantum case. The quantum case, considering the quantum case for this in these slides, the quantum case, we have the same first law of thermodynamics. However, here, the heat, we change the amount, the population, and for the work, we change the energy levels, okay? I'm not presenting the calculations to get this generalized Maxwell relation is in that paper that I presented at the beginning of the talk, okay? Here, we have the entropy, and lambda is a working parameter. It's like the magnetic fields. Temperature, and here, this quantity here is the thermal average of the Hamiltonian, okay? By integrating this result here, we get a very similar result as the previous equation that I presented before. And I will study this equation in two cases. So the goal of this work is to measure this length here. That's exactly the amount of heat exchanged with a thermal reservoir. Okay. However, for this quantum case, let's see two cases. Okay. Here's the generalized case. And here is a supposed Hamiltonian for a certain case. Let's consider a spin case, a condensed matter case. Okay. Here's an internal Hamiltonian. Let's suppose a Heisenberg Hamiltonian, Dzielozinski-Moria Hamiltonian, Heisenberg, Ising, contributions without magnetic fields. Okay, spin-spin correlations. And here, as a second contribution, is a mean fields contribution. A mean fields contribution, we are making this Hamiltonian a classical Hamiltonian because we are considering that all spins are interacting with all of the spins. It's an average Hamiltonian. Okay? If we consider that the working parameter is the magnetic fields, and making this derivative here, the result is exactly the magnetization. If you place back the result inside this term average, we will recover the classical case. And it's reasonable because when we have a classical Hamiltonian, because we are considering average Hamiltonian, the magnetization contains the local correlations. Okay. Let's suppose another Hamiltonian. Let's suppose a case when we have spin-spin correlations, such as Heisenberg Hamiltonian, and a Zeeman term. Okay. And as a working parameter, let's suppose that's the J, the magnetic interaction. It can be strange that the working parameter is the J. However, I will explain further in the talk that the J depends on the pressure, a pressure applied to the material. Okay. If you considering this result here, you make a derivative of the Hamiltonian with respect to the J. The result is exactly as here. The bracket is a thermal average. Okay. This spin-spin correlation, thermal correlation, is a magnetic susceptibility. It's a textbook for magnetism. Okay. And at the same time, it is the quantum discord. It is explained here in this book. Sorry, in this article. Okay. Using this equation here, you see that the isothermal entropy change is connected with the quantum correlations, considering these kinds of Hamiltonian. And for this case, when the parameter here is the susceptibility, and the susceptibility contains non-local correlations. So we can measure the isothermal entropy change contains information about the quantum correlations. For this case, for non-local correlations. Okay. In the case of the susceptibility. Okay. To use experimental data here, I will open a parenthesis to explain a bit about the metal complexes. That's the materials we are using to study to use in this work. Metal complexes. This is a special case of materials. These are not ferromagnetic materials. These are not ferromagnetic materials, and these are not paramagnetic materials. These are in between. These are clusters. These are clusters. Can you click, please, here in this icon here, clusters? For example, here we have a crystal structure of this material. Here is the chemical formula. The metals here can be manganese, iron, copper, and these metals are here in these green dimers. These are only dimers. Dimers spaced from all of the lattice of the material. And there is no interaction between this dimer and this dimer here. So these materials are in fact a dimer of spins. And the spin, for example, for copper, it's a 1/2 spin. These are 2 spins, one half. Okay, can be 2 for iron and 5/2 for manganese. Okay, without interaction between the dimer. Okay, can you close, please, this window and open the chain 1? Chain 1. It's only an example. It's another structure. And along with this chain here, we can see the manganese. There is a manganese ions along with this chain, and there is no interaction between this chain. It's a true one-dimensional magnetism for manganese. Can you close, please? And open chain 2, this one. Here is another example with a chain of cobalt. Here inside this octahedra, there are several ions of cobalt. Okay, can you close, please? Okay, these are examples of the low dimensionality of these materials, and you can use these materials the data of these materials to verify the model we are producing. And there are several Hamiltonians to understand these materials. Heisenberg, Jalosinski-Moria, where the spins can be orthogonal, local magnetocrystalline anisotropy, and so on. Here is a very simple example. We can do this very simple model for this material. One dimer, spin 1/2, 2 ions, only 2 ions, spin 1/2. It's a quantum mechanics problem, a very simple from undergrad. And we can make this Hamiltonian that's written here in blue. We can make this Hamiltonian, diagonalize the Hamiltonian, and obtain the eigenvalues. Very simple problem. And the Hagen states is 1/2 plus 1/2 is 1. You have a triplet. 1/2 minus 1/2. We have the singlet states. So we have the singlets and the triplets. It's important for the future that I will discuss. Can you click in this icon here, please? No, it's not this one. Can you close, please? Can you close, please? And this one. From that eigenvalues, we can write the susceptibility. That's here is a very simple. It's a closed expression. Can you close, please? And can you click here in this flag? And here are the susceptibilities as a function of temperature for all of the experimental data of the materials with the theoretical results, the solid line. And it's not. Can you scroll down? Scroll down here. Can you scroll down here? And here are the free parameters. we can obtain the free parameters. So it's a simple. You can obtain the parameters. That will be important for the future. Okay. So it's simple to handle these materials. You can use the parameters. You can use these materials to apply in the models, as you see in a few minutes. Okay. Can you close, please? Okay. Okay. Let's return to what we were discussing. Okay. The result we had was the entropy change as a function of the quantum discord. I mean, the quantum discord contains an amount of entropy. Okay, that was the previous result, and I open a parenthesis to present what the metal complexes are. Okay. And what you have done to try to connect with the experimental results. The same material I was presenting, what you have done, can you click please here in this icon here, please, this one. Here is the exchange interaction for the Heisenberg Hamiltonian as a function of pressure. As a function of pressure, you see that increasing pressure, we change the ground state from the singlet to the triplet. We change from this state to this state. Okay, that's the. Can you click out, please? You change from this state here, singlet, to this state here. You can change the quantum discord of the system. So it's possible to see a difference in this amount of entropy change applying a pressure. It's expected. Okay. Can you please click here? So here is the quantum discord as a function of temperature for that material that I presented, because we know a lot of values of J from the first principle calculations, and the quantum discord only depends on the J value. So it's possible to obtain all of these values. And from these results, it's possible to calculate the entropy change. Okay. Can you click out, please? And click here, this last. Okay. And here's the entropy change, the amount of heat that the system can exchange with the thermal reservoir as a function of temperature, depending on the ground state. Here's the ground state is the singlet. In fact, the singlet contains much more quantum correlations. Here's the ground state is the triplet that has much less quantum correlations. In fact, it was predicted by that equation that's behind here. Okay. Okay. Can you click out, please? Okay. You can. No, I can do this. Yeah. Okay. For the adiabatic process, it's a similar idea. It's a similar idea for the classical case. For the classical case, the material is isolated from the environment. It's isolated from the environment. When we apply a magnetic field, the temperature increases. However, we are considering two contributions for the entropy. It's very important to consider two contributions for the entropy, because when we apply a magnetic field, the entropy of the spins decreases. And we need a second contribution, that's the lattice contribution, because the lattice contribution needs to increase to keep the total contribution constant. That's the reason, because when we apply magnetic fields, the temperature increases. That's the reason when we apply a pressure in a gas, the temperature of the gas increases, because you need at least 1 minute more. That's the reason when we apply a pressure on a gas, the temperature of the gas increases, because you need at least 2 contributions of the entropy, because one contribution decreases and the other needs to increase to keep the total entropy constant. Here, the phonon's entropy is increasing. That's the temperature of the system increasing. Okay, and here is the amount. Here's this result comes from the classical thermodynamics. Is the amount of the temperature increasing, okay? And our goal was to obtain a very similar result from the quantum thermodynamics. Considering my time is over, in fact, for the quantum adiabatic process, this work is an ongoing work, and I don't have connections with experimental results to present, because in fact, it's an ongoing work, and I do hope to have results for the next months. But we have a closed expression very similar to the classical one. In fact, it depends on that thermal average of the Hamiltonian and the variance of the Hamiltonian. And it's only a few words I have to this quantum adiabatic process. That is this length here, the amount of temperature that the system increases in this adiabatic process. Okay, as a main conclusion, our goal was to determine this isothermal entropy change and try to connect with experimental data. And the adiabatic temperature change is only our ongoing work, and we need further interpretation and data. Okay, thank you for attention.
Okay, thank you, Mario. We have time for 1 or 2 questions.
Hi, Mario. Thank you for the talk. And then one thing that I didn't get is how the spin influence, the value of the spin influence your results. Because you have this possibility of a spin 1/2, spin 2, and spin 3, or any other of your complexes. But how the value of the spin can affect the results? It can increase, because in the past we did some studies on that.
Yeah.
And the value of the spin was highly influential, because the higher the value, the smaller the correlation.
Yes. One student is doing it numerically for a while.
I see.
These calculations is for 1/2 spin. But we have one student that is doing the same calculations for, however, numerically.
I see.
It's an ongoing work.
Okay, thank you. Thank you.
Hi, Mario. Thank you for the talk. I would like to know if to get the adiabatic temperature change, you could use the isothermal entropy change and just calculate the specific heat and introduce in the equation.
For the quantum case?
Yeah.
I don't know for a while.
Because you can do this classically.
Yes. Because it depends on the variance of the Hamiltonian, and it is the specific heat, probably.
Okay, thank you.
Okay, so I think that we can thank again Mario. So we are a bit late on time, so I'd say let's try to come back at 2:30 instead of 2:15. So we have 15 more minutes for lunch time. Okay. See you guys.
Som, som. 1, 2, som. Testando som. Som, som. 1, 2, som.
Yeah, yeah. So basically,
Okay. So we can start our afternoon session. So Gabriele De Chiara is going to talk about thermodynamics of quantum time crystals. Thank you very much. And the word is yours.
Thank you very much, Fernando. It's a pleasure to be here at this fantastic conference. Thank you for the invitations from the organizers. Okay, so today I'm going to talk about quantum time crystals, and I wanted to first do the same that other people did to put where I come from on the map. So this is Ireland, the green spot, and then Belfast is somewhere up in the north, and this is our beautiful campus. Okay, so let me start discussing about time crystals, and we know very well about space crystals because we studied this maybe in undergraduates or even in school, and we saw a lot of these structures this morning. So when you have interacting particles, they can self-organize and form these spatially periodic structures, which we call crystals. And so the questions arises whether we can find systems, classical or quantum, that can self-organize in time, so that you have periodic repetition of certain physical properties. And this was a question that probably was addressed for the first time by Wilczek. And he was thinking about a charged particles in a magnetic field that would start rotating spontaneously. But then after probably 1 year or less than 1 year, there were no-go theorems that said this is impossible if you look at the ground state of a quantum system or if you look at equilibrium states in either classical or quantum systems. So there must be something else. There must be some driving in your system. You must bring the system out of equilibrium. And one quite popular class of these time crystals that were initially proposed and then realized was these discrete time crystals, where the system is driven periodically with some kicks, with some changing the Hamiltonian in time. We can think of this as a very simple cartoon where if you think that you have a spin system with some interactions, you can prepare them with a spin flip pulse, you can prepare them in this down, down, down state, and then with some interactions, and you need some random disorder that prevents the system to thermalize, to self-thermalize. Then if you wait some time and then you spin flip, then approximately you'll get all these spins pointing up. Then you repeat the cycle, and then you let them evolve. They don't equilibrate because there is some many body localization, for instance. And then after some time, you do the spin flip again. So the net result is that we did 2 cycles of these evolutions, but we see that the period of these oscillations of the magnetization is actually 2 times the period of each one oscillation. So there is a period doubling here. And so there is a spontaneous symmetry breaking of time invariance. The system is driven with a period t, and the system responds to that with oscillations at period 2t. Normally, if you drive a system with a frequency, you would expect, to some approximation, the same response at the same frequency, not at half the frequency, which is what's happening here. And these discrete time crystals were realized now in many systems. NV centers, this is Michel Lukin group, other NV centers later. This is trapped ions from Chris Monroe group. These are some atomic ensembles in cavities, and then these are superconducting qubits on the IBM Q platform. Right, so that class, I call that, so people call them discrete time crystals because there is this discrete symmetry which is broken, but you can also break a continuous symmetry, which is actually more in the spirit of what Wilczek probably had in mind. Time is continuous and we want to find something that breaks this continuous translational symmetry. And so to do that, as we said before, you cannot just have equilibrium systems, so you need some driving and dissipation. And in this case, it's a time-independent Hamiltonian and in the presence of dissipation. And again, the dissipation is time-independent. So all the system is regulated by an evolution which is time-independent. The Lindbladian, if you want, is time-independent. But the system exhibits a long time cycle limit where there are oscillations for long times. And this happens in the thermodynamic limit when the number of particles is growing to infinity. And this leads to persistence oscillations, which are not imposed externally, like in the case of discrete time crystals, where you have a periodicity and the system responds to half the periodicity. Here, there is no periodicity. And the periodicity is an emerging feature as the number of particles grows to infinity. And here are two examples of two experiments, one with a BC in a cavity where these oscillations were found, and this is another atomic systems interacting with lasers, no BC, no cavities, but where the system exhibits these persistence oscillations. Okay, so this is the outline of my talk. I'm going to talk about these continuous time crystals, dubbed boundary time crystals sometimes. I'm going to talk about the microscopic model, the thermodynamics, and if I have time, I'm going to talk about more than one time crystal, so two time crystals coupled. Okay, so let's start with the basic model of these continuous time crystals. So everything is time independent, and Fernando and Saro and co-workers, they call these boundary time crystals. And we start with an ensemble of spin 1/2. These V operators are the normalized total angular momentum operators. They fulfill the usual commutation relations. And this is the simplest Hamiltonian. It's a Hamiltonian of an effective magnetic field along the x direction. So we are looking at the total magnetization V of the ensemble, which, as you can imagine, will start, due to this Hamiltonian, will start to precess around this effective magnetic field. And then we add some dissipation, and this dissipation is described by Lindblad master equation. So typical thing, we have seen this many times in the talks in the conference, where these V minus and V plus are the usual ladder operators for spins transitions in the ensemble. As a new thing compared to what Fernando and Saro did in the previous paper, we are adding temperature. So we are adding not only the dissipation downwards, but also the pumping term, with this N beta, which is proportional to the temperature of the environment. Right, so originally the model by Fernando and Saro was with 0 temperature. So we are at the temperature to see if time crystals would be robust to thermal fluctuations. And as you can imagine, so as I said before, the Hamiltonian is tending, so it's trying to induce some rotation, some precession of V around the magnetic field, while the dissipation would like to align the magnetization along the axis. If you were at 0 temperature, you will get the ground state for long time limit, but because there is the magnetic field, this will keep oscillating. And so if omega is large enough, then you will get persistent oscillations. This is a little bit the idea, right? But this only emerges in the thermodynamic limit when the number of particles goes to infinity. So if you have a finite system, the system will eventually decay to a steady state. And you can think of this, so this is not an abstract model, but you can look at microscopic models based on quantum optics systems, so driven emitters in a waveguide. And I will discuss a little bit later. This is intrinsically a local master equation. Again, we had a talk from Emmanuel this morning talking about local master equation, so I will talk a little bit about that. Okay, so to start with the description of this, we're going to go to mean field. This is a spin ensemble, no interaction, so mean field should actually work very well. And we can look at the mean magnetization. So this is the renormalized magnetization along each axis. And we can go to a thermodynamic limit and take the average, and this is the mean field. Once you do this, Fernando and Saro, they show that the magnetization will fulfill this three simple differential equations. So these are all first-order differential equations, but crucially, they are nonlinear. And being nonlinear, it will give is a dynamical system that is nonlinear, and then it can give rise to interesting results. If it were linear, you will never get a time crystal. But what we found is that these equations that were previously derived in the zero temperature case are identical in the case with temperature. So temperature doesn't enter these equations at the mean field level, and therefore the phase diagram of the system, whether you are in a time crystal or not, doesn't depend on temperature. And so our first result is that time crystals at the mean field level are robust to thermal fluctuations, which is good news because this means that they are robust, and in the experiment they will be easier to observe. Okay, so if we look at the equations, there are two conserved quantities. One is the magnetization is always conserved, and then there's this other more exotic quantity which is also conserved, and I'm going to use this later in the when showing the plots. And we fix the maximal magnetization, which means that at time zero the spins are pointing along one particular direction. Okay, so if you do the calculations for finite number of particles and you look at the magnetization, for instance, along X, we see something like this, that for a small number of particles, there is a decay time, but as you increase the number of particles, the decay time is increasing. It's increasing, and then in the limit of n going to infinity, you can recover the mean field result and get this limit cycle. So it's a periodic oscillations that persist in time. This is kind of similar. I kind of reproduce myself the results from Yemen. It's not exactly the plots from their paper, but it's very similar. So how do we establish whether the system is in a time crystal or not? We have to look at the spectrum of the Liouvillean. So the system has a Hamiltonian and the dissipative Limbaugh master equation. If we look at the spectrum of the Liouvillean, there is always one eigenstate with zero eigenvalue. This is the steady state. And so in the long time limits, for any initial state, you always go to the steady state, no problem. But if we look at the smaller eigenvalues, we will see that they will have a negative real part, which means this is the part that is responsible for the decay, and then they will have an imaginary part, which is responsible for oscillations. And now what happens in these systems is that when omega is small, there is a gap here between the lambda equal to 0 and the next one. There is a finite gap. But as you increase omega, this gap disappears. And there is a sort of collapse of all these eigenvalues with negative real part to the one at lambda equal to 0. The gap is responsible for the time, for the lifetime of the oscillations of the crystal. And so as this gap is going to 0, the lifetime goes to infinity. So this is, if you want, another way of seeing the mechanism from the spectrum of the Liouvillean. Okay, this is a little bit more technical. If you want, we can choose an ansatz to solve these equations where we can easily set mx equal to 0. So this is the magnetization along the field, so we don't care about that. And we look at the magnetization in the perpendicular plane, my and mz, and we can put an ansatz where we put this function of time that we want to find. And what actually Federico, Carollo, and Igor Lesanowski in this paper found was that, okay, in the normal phase, this f becomes constant. In the time crystal phase, which is when omega, the Rabi frequency, the effective magnetic field over the dissipation, when the ratio is equal to 1, this is the critical point, and when omega is larger, you get into the crystal phase, and this f of t will actually lead to persistent oscillations. So this is a little bit the explanation. The form of f of t is not very simple. It's not just omega times t, but it's a little bit more complicated. Okay, so that was mean field. Sort of classical, if you want, because we are still at the mean field level, but we can go beyond that and look at the fluctuations around the mean field. So we look for the fluctuations of the operators V around the mean value, and we call these F operators. And these F operators, their commutation relations is actually similar to position and momentum. So later on, I will use this to describe the fluctuations in terms of Gaussian or bosonic formalism and so on. And we will look later about this covariance matrix. Okay, so let's talk about now the thermodynamics, and this is maybe related closely to the topic of the workshop. So it's a local master equation, and that means that the jump operators V minus and V plus, These are jump operators that flip all the one or more spins, but the Hamiltonian is not Sz, it's Sx. So the jumps are not between eigenstates of the Hamiltonian, but are between other states. This qualifies this as a local master equation. And this is an infamous category of master equations because they might, so if you're not careful enough, it seems that it can violate thermodynamics. But any dissipative process described by CP map is a physical system. So we know in this community, I don't have to say these things, but if you have, we had in the talk by Alexander the first day, you can engineer everything with quantum systems, okay? So are those compatible with thermodynamics? Yes, provided that you do the correct analysis. And you need to have a microscopic model. You can choose any microscopic model. My favorite microscopic model is the collision model, where the bath is schematized by a sequence of small units, can be qubits or oscillators, that interact for a short time with the system and then are discarded. And as you do this mechanism, you can reproduce the master equation. Now, I'm going to show some of the formalism, but probably because of time, I'm going to go quick. So here we chose harmonic oscillators that interact for a short time, and they interact with this kind of exchange interaction with the spin ensemble, and then they are discarded after that. We assume that the units, these environmental units, are in a thermal state. This is crucial. Then we evolve in time with the time operator, with the time evolution operator, and then we take this kind of difference of the new state after the collisions minus the old state before the collision divided by delta t, take the limit of delta t going to 0, you expand this to second order, etc., and from this, after some algebra, you get the master equation. So this is a way in which you can not only theoretically, but also experimentally simulate or realize the master equation, okay, with quantum computers, for example, or quantum simulators in general. Good. And now, since we have a microscopic model, then I can do thermodynamics, because I can calculate everything from the microscopic model, and we know approximations. And for instance, I can calculate the heat, and the heat is this is the energy of the environmental units. This delta rho is the state after the collisions minus the state before the collision. So this is the energy difference of the ancilla of the environmental unit before and after the collisions. With a minus sign, this will give me the heat exchange with the system. Okay, so quite simple. And if you put everything from the master equation into it, then we found that these are actually related. This is Q dot, so this is the heat current is related to these expectation values of V minus V plus and V plus V minus, which are observable quantities. So they depend on the magnetization of the system. So I can use the mean field or the fluctuations to calculate, but even experimentally measure these quantities. So this is, okay, it's another of our major results. We can connect heat current with observable quantities from, if you realize this experimentally. You can see that this is kind of reminiscent of a detailed balance condition. So the system would thermalize if this would be satisfied, but this doesn't happen because there is always a constant driving in the Sx. The system doesn't thermalize. It would thermalize if the local Hamiltonian would be 0. If Sx, so 0 magnetic field, it would thermalize to this, but it doesn't, so you continue oscillating if you want. Okay, and using the same logic of this, you can calculate the internal energy change. And again, this is related to this magnetization. This is like a second order, and this is a first order. And when you take mean field, this can be neglected. So this will only be important when you take the mean field. So we have the heat, we have the internal energy, and therefore we also have work. Remember that the system is driven, so there is an external work that is used to run, if you want, the evolution of the system. And this is compatible with the first law. So you get automatically, from our formalism, you get automatically the satisfaction of the first law. There is no violation. Yes, and the bottom line from this slide is that all three thermodynamic quantities be connected with observable quantities that can be measured. Okay, and these are a little bit the results. Here I'm plotting the work power, so the derivative of the work per particle. So it's not normalized. This is always positive. We are in the stationary phase as a function of time. It's always positive. So work is always injected into the system, and heat is dissipated to the bath, no matter the temperature of the bath. And in the time crystal phase, instead, you get typical oscillations of the time crystal phase as a function of the number of, so for different number of particles, as you grow, you go into the mean field, which is this dashed line. And again, this is always positive. Work is always injected into the system and dissipated. Okay, we can integrate the power from 0 to t, and as a function of omega, we find a sort of phase diagram where we have the stationary phase and the time crystal phase, and in the mean field, we see this nice cusp, which signals the non-analytic behavior at the phase transition. Depending on, you remember I had a conserved quantity C, so depending on C, you have different results in the time crystal phase, but the cusp is always there, regardless of the value of C. Okay, the other thing, and this was mentioned this morning and yesterday as well, to check if thermodynamics is consistent, you want to look at entropy production, and Gabriel and Mauro are the expert here, but okay, also other people before talked about this. So you can define the entropy production per the collision as the mutual information I between system and environment after the collision, and the conditional entropy between the state of the ancilla before and after the collision. Because these two quantities are positive, non-negative, then the entropy production is by construction non-negative. So this automatically fulfills the second law of thermodynamics. So this can be cast in this way, where delta S is the, so after some algebra, all of these can be reduced to this simpler formula, where delta S is the change of entropy of the system, and phi is the entropy flux, and this, again, is non-negative. So the entropy flux is this quantity here, and yesterday we were discussing about the origin of the entropy. So this is all informational origin. I don't know, I don't see Sebastian is somewhere in the audience. If you take rho to be a thermal state, like we do, you get here a e to the minus beta h, and if you do the algebra, then this entropy flux is just proportional to the heat. So, and that means, yes, while delta S, yes, is the system entropy. So in our case, since the bus is thermal, phi dot this entropy flux can be associated with Q dot, but Q dot, as we saw in the previous slide, can be measured. So the entropy flux can be measured in this way, assuming always that the bus is thermal. So we can measure the entropy flux. What about delta S? Can we measure the system's entropy? And okay, if you look at this in the mean field level, the state is pure. Is all the spins up along some direction moving on the block sphere. So everything is pure. But if you go beyond mean field and you look at the fluctuations, then you can start looking at the entropy. So the entropy for the pure state, of course, is 0. So you have to go to the fluctuations. And as I said, these fluctuations fulfill these bosonic commutation relations. But it's like you have 3 axes, because you have Sx, Sy, and Sz. But there is a mean field among these. There is a direction, which is where the spins are pointing. If you go in that direction, then they become like position and momentum operators of a harmonic oscillator. Then, okay, you look at Gerardo's papers, which explains these things much better than I'm doing it now. And if you do all this formalism for Gaussian states, you see that you just need to calculate these eigenvalues of the matrix M, which is this product of the two covariance matrices for these operators F. And once you do that, then the von Neumann entropy can be calculated like this, where this lambda is one of the eigenvalues of this matrix M. So bottom line here is that measure bosonic fluctuations. So these are observables, in principle, of the magnetization of the spins. Do your homework, so calculate these eigenvalues of M, and from this you calculate the von Neumann entropy. So bottom line, also for this, we can associate the entropy with measurable quantities, and therefore everything. So the first law can be observed experimentally, and the second law can be verified experimentally. Both the two laws can be connected with experimental quantities. Okay, these are some of the results for the entropy in the stationary phase as a function of time, in the time crystal phase as a function of time. Here, the entropy saturates to some steady state. In the time crystal phase, there is a divergence that goes logarithmically with time. And this is because the variance of these bosonic fluctuations diverges logarithmically, with a power law in time, and this translates into a divergence of the entropy logarithmically in time. Okay, I'm gonna skip this, and this is this is the integrated von Neumann entropy as a function of the parameters, and you can see in the stationary phase this converges to a steady state, and then you have this sort of order parameter in the time crystal phase. And as I said before, there is a logarithmic divergence of the entropy as you increase n. Good. Okay, I'm doing good with time. So let's talk about fluctuation theorems. And again, yesterday we saw some of these discussed for the entropy production. So I'm going to say basically what I'm going to talk about in the next few slides. So we are going to talk about the stochastic entropy production sigma, which is the entropy production for each stochastic random process in the system. But remember that now the system, and this quantity for classical systems or for quantum systems with no coherencies, they fulfill these detailed fluctuation relations, the Crookes relation, or these integral fluctuation relations, which is similar to Jarzynski relation, but for the entropy. But here the problem is that the system is coherent, and therefore you need to do some adjustment to these theorems. You need to define sigma in a clever way so that you recover these theorems. And this was done partially in this paper by Crookes from 2008, and more recently by Kwon and Kim in 2019. So this is going to be a little bit technical. We assume that we have an initial state. We don't make any assumption on the initial state. It doesn't have to be thermal, it can be any state. Then we have a generic channel described by these Krauss operators. We don't make any assumption of weak coupling, strong coupling, equilibrium bus. It can be anything you want, as long as it's a CP map. And we assume that there is a fixed point. This is the fixed point of the map. And with this, one can define a quantum reversed map, which is a sort of inverse of n, with these Krauss operators K and K daga, which are related to the inverse of the Krauss operators, but transformed by these by the fixed point of the map n. This is sometimes called this Petz recovery map. If you use this, then you can prove the fluctuation theorems. And I'm going to do quickly. So we need the spectral decomposition of the initial state. So this is the eigenstates of rho, the final state, and these are the eigenstates of the final state after the map. And then we also need the basis of eigenstates of the steady state. So if you have a generic process where the system goes from an initial eigenstate of rho to a final eigenstate of n of rho, you can define the stochastic entropy, the single shot stochastic entropy like this, so that if you average over all these probabilities, then you get the normal entropy. So this is the entropy change of the system every time that you do this process. You get a random number. This is the random number, delta S. So I define the stochastic entropy. The other thing I need to define is the heat, the stochastic heat for each of the transition. But the problem is that it may be that rho, the initial state rho, has some coherencies in the basis of the steady state, and n of rho can also have some coherencies in that basis. So if we are looking at equilibrium and you have a state which is diagonal with the Hamiltonian, etc., you don't have any quantum coherence. It's the same as a classical system. And you can derive these fluctuation relations much easier. Here, because you may have coherencies of off-diagonal elements, you have to take this into account. And one can look at this kind of process where you jump from a coherence of the state rho from ij in the basis of this. With n, you go to a new state kl off-diagonal. For this particular process, it's a weird process because it's off-diagonal to off-diagonal. We define this they define this, Kwon and Kim, they define this quantum information exchange delta Q, which is related, you see, with this logarithm, is related to the populations of R of the steady state. So if this is all a diagonal state in the Hamiltonian basis, this is just heat over temperature, beta Q. So it's very simple. But this is the generalized version when you have non-diagonal states. And now that I have defined all these quantities, then I can define sigma, so the stochastic entropy production with this process. It's a little bit crazy. You have these 6 indices, and you can define this as the difference of delta S minus delta Q that I've defined there. And when you do the calculations for this stochastic entropy production, you can define a quasi-probability, a complex quasi-probability. And here you have to think like this. So we are starting from rho, which is in an eigenstate mu, with some probability P of mu. Then we project on the left by pi, on the right from pi j. So it's not a projective measure, but it has this left and right projector. Then you evolve in time, project again from the left and from the right, pi k and pi l. And then you do the final projection on the final eigenstates of the final state, okay? If you are still with me, you can define this quasi-probability distribution in the same way as you do the work distribution. So you introduce this delta function for values of sigma, and you sum over all probabilities that give you that value of sigma. You do this, and then you can prove this generalized Crookes relation and the integral fluctuation theorem, okay? What you notice there is that the probability for each of these processes is complex, and while this quasi-probability distribution P is actually real once you sum over all, but it can be negative. So it's still a quasi-probability distribution. It's not, say, a typical, generic probability distribution. And so these are the results, finally. So you can kind of wake up again after this technical part. And we looked at this quasi-probability distribution for sigma in the stationary phase and in the time crystal phase. And what we see is that in stationary phase, P of sigma is always positive. In the time crystal phase, we see tiny, tiny negative parts, which are not, say, rounding errors. So these are actual values, very small, 10 to the minus 5, but still there. And so we kind of claim that these negative parts of the quasi-probability distribution are an indication of the time crystal phase, and that don't happen. We don't have an analytical proof of this, but we have strong indications that in the stationary phase, this doesn't happen. In a sense, because you have a more coherent evolution in the time crystal phase compared to the stationary phase. And if you want to know more about quasi-probability distribution, then with Stefano Gherardini, we wrote recently a tutorial published a couple of months ago. Okay. Good, so I have some time and I can come to my last part of the talk where I'm going to talk about coupled time crystals. So here I take 2 of these objects coupled together, and what we want to do with this system is first to see the dynamics, the thermodynamics, and in the thermodynamics what we applied this was to charging batteries. So we're going to use 2 of these spin ensemble to realize quantum batteries. So how do we do that? So we have the 2 spin ensemble. Again, with this Hamiltonian, we assume that each of them is driven by our laser. And if you go in the rotating frame, you get a similar Hamiltonian than before, but you get both the Sx and the Z. Okay, it's a tiny change compared to the other case. And then we assume that both so the 2 spin ensembles are coupled with this exchange and Ising type Hamiltonian, XX, YY, and ZZ. And we assume that each of them is coupled to a bus, possibly at different temperatures, like a hot bus and a cold bus. And we assume these, again, these collision models that give rise to the master equation like before. So each one of them has its own local master equation with some temperature Nj. And quality here is not great, but this is results taken from a paper by Fernando, where he was looking exactly as the system, but at 0 temperature. And the nice thing is that you have different phases. You have a normal phase where both ensembles decay to a steady state. You have a time crystal phase, which is synchronized, where these oscillations, I know it's a little bit faint, but these oscillations from the 2 ensembles are synchronized. They go in parallel. Then you have a chaotic, non-periodic, quasi-periodic result where there is no evident periodicity in this system. And then you have, again, another type of time crystal where you have period doubling, where here now the 2 magnetization going up, out of phase, in opposition of phase. So there is a period doubling in the oscillations. So we wanted to look at applications of this for batteries. And first we consider a scenario in which that we call parallel charging, in which both of the two spin ensemble form the battery with coupled batteries, and these external lasers provide the charger. So they inject work into the system, and this charges the battery. Remember that these are still coupled to the bus, so there is heat which is dissipated and lost into the environment. And if you look at the function of the J and JZ, these are the couplings between the two buses, we see the two different phases in the stationary phase and the time crystal phase, and we see brighter colors. Sorry, this is the integrated power, the quantity that is plotted, and you see that this quantity is much larger in the time crystal phase than in the stationary phase. So this is the first result. So we get better. This is still the work absorbed by the system, but we see this is larger in the time crystal phase. And the other thing is that we see again this cusp appearing at the phase transition. This is not yet the charging of the charged power, is still how much power is absorbed by the system. So to look at the performance, so we look at the energy stored, which is then this energy that is stored there. And this is the final row minus the initial row. We measured with some Hamiltonian. Okay, you are free to choose these. We chose the free atomic Hamiltonians of the two ensembles, which makes sense once you switch off interactions and once you switch off the lasers, this is the Hamiltonian that will remain. The other quantity that we look at was the charging efficiency. So this is not the typical charging of batteries in the closed system, but in the open system. So there is heat that is dissipated into the bus, and we wanted to know how much, so what's the ratio between the energy, the charging energy E, the energy stored, divided by the amount of work that you put into. So this quantity is always less than 1. It gives you some sort of efficiency in the charging. And as a function of the parameters, we see this kind of behavior. This is for the energy stored. In the time crystal phase, this is much larger than in the stationary phase. And then we see in the middle, we have this sort of sudden jump due to some instability where the system, depending on initial state, can jump from time crystal phase and to the stationary phase. So this is a region of coexistence of the behaviors of time crystal and stationary phase. And then if you look at the function of time, so this is the energy stored as a function of time. Solid red is the time crystal, and this dashed blue is the stationary phase. You can see that the time crystal phase is has a much larger energy stored peaks in time. So there will be much more, there will be much storing power in time crystals compared to the stationary phase. But also, if you look at the efficiency, then we see, again, efficiency decays initially from 1 to small values, because at 1, there is no heat that has been dissipated yet. And then there is a decay for both the time crystal and the stationary phase. But still, we see that for the time crystal, we always get an efficiency which is larger, at least the peaks are larger than the stationary phase. So time crystals are better at storing energy and doing that in a more efficient way compared to the stationary phase. So this is the conclusion for this part. We also looked at another system, similar, where one of the two ensembles is not coupled to the laser. Only one of the spin ensembles is coupled to the charger. And what happens is that this laser induces time crystals in the first ensemble, and due to the interaction, it's possible to induce the same time crystals in the other ensemble, which is not driven, but is driven by the other one. And this is something that Saro, in another paper, discussed as seeding crystallization in time, and we exploited this concept to have this battery now on only one of the two, while the spin ensemble and the charger corresponds to the, and the laser corresponds to a charger. So it's slightly different result. I don't have a lot of time. The phase diagram here is maybe much more interesting. We have stationary phase, time crystal phase, quasi-periodic phase. We have a time crystal phase that depends on the initial state of the system. So depending on whether you are, it will be time crystal or stationary. So these kind of bistable results. And our conclusion here is the same. The stationary phase is not very good at for storing energy. The time crystal phase is much better. Here there is this quasi-periodic or this unstable phases which have large energy stored, but they are unstable. So it's not probably not the best to use these for the batteries. It's better to use the time crystals. Okay, and with this, I'm coming to the conclusions. So just a summary, our results in the first part, I was talking about boundary time crystals, and our first result was that time crystals are robust to thermal fluctuations, at least in the mean field description. And I also showed that thermodynamic quantities, so heat, work, and entropy, can be connected to observable quantities, so they can be measured in experiments. I've talked about the stochastic entropy distribution and fluctuation theorems for this generalized entropy production. And then in the last part, I talked about coupled time crystals for energy storage, so for battery charging. So if you want to know more, these are the two papers. So the older paper is basically the first part, while this recent paper that we put on the archive is the last part on battery charging. Let me thank my collaborators, Paolo and Igor from recently moved to Coventry, and Mauro Antezza from Montpellier. And with this, I thank you for your attention.
Thank you, Gabriele. Okay.
Thank you, Gabriele. I have two quick questions, both of them regarding to the signature of
time
crystals in in that distribution that you showed.
Yeah.
So one of them is that like is it possible that the negative values are related to that small part of the U dot that you disconsider? That's the first question. And the other is, typically in situations like this, you can eventually find signatures of transitions in differences on higher momenta, like instead of just the distribution, like spread of the distribution or things like that. Does it happen here as well?
Okay, two interesting questions. The first one, so this is exact for a small number. So here we're not neglecting anything. And I think you may be right in the sense that at the mean field level, you won't see this. So this is exact calculations with 10 spins. And the system has to be really coherent for you to see these things, okay? In this paper, we actually look at simpler systems with 1 or 2 qubits. And we see that if you start with a system that doesn't commute with the Hamiltonian, and the Hamiltonian is changing time so that the initial and final Hamiltonian don't commute, then you would observe these and you will observe much larger negative values, okay? So your system has to be as much coherent as possible. I have the impression, as you say, that if you go into the mean field, then these things completely disappear. The second question, I probably don't know the answer. Can you repeat a little bit?
So you looked for a signature in terms of these negative values, but like sometimes we can so the distribution itself, the spread, higher momentum of the distribution sometimes shows a signature as well.
Yes, I agree with you. But again, because the system is quite small, it might be hard to see these very large values. So bottom line, I don't know. And I guess that if you go into larger system, we might be able to see this, yeah.
Hey, Gabriele. So the existence of a time crystal does rely on the kind of the collective dissipators, right? And if you had dissipators that were not, the same game as in superradiance, when you have dissipators that are not that collective, and eventually you lose the superradiance, do you think you also lose the time crystal phase? And then my question actually is, do you think one could study that with collision models? Because in the collision model, essentially, you always have to assume that you couple to all of the qubits equally, right?
Yes, but I wouldn't exclude the existence of the time crystals. More like you're thinking about the Twitch spins. I wouldn't. I don't think there is a no-go theorem on this. So I think that if you had some cleverly designed model, I think you should still be able to see something. So this is a conjecture, okay? So I don't know, but I wouldn't exclude it a priori.
I always thought it was very much related to the same things that generate superradiance.
Yeah.
And you do lose superradiance if you have local dissipators.
I don't know. The short answer is I don't know. I wouldn't exclude it.
Okay, thank you for your great talks. And I wonder, because the readability and have some corresponding unitary operator for with the purification. So I want to ask, there is some difference between the two unitary operator corresponding to the time crystal phase and stationary phase. And so one thing I want to add is, because you did you simulated the phase change with the several system size. So I think so you can calculate the exponent of this phase transition. So, but you didn't show it. So, is it or not?
You can calculate. Sorry, can you repeat?
The exponent.
The critical exponent.
The critical exponent.
Yes. Yes, this is in the paper by Carollo. Maybe it's also in Fernando's paper, I don't remember, but the scaling of the divergence of the fluctuations is definitely in that paper by Carollo and Lesanowski. Yes, and they have some critical exponents there. Was it in yours as well?
In mine,
no.
there was. But in Carollo, yes, that's true.
What was the first question again?
Because the unitary dynamics is corresponding to the unitary equation is a purification, right?
Yes. The collision model, you mean?
Yeah.
Yes.
There is a difference between the two unitary dynamics corresponding to the crystal phase and the stationary phase.
But I'm not sure I understand the question. So if I understand, the unitary operator will map this to the Lindblad equation, but the Lindblad equation is the same for both the time crystal phase or the stationary phase. The Lindblad, okay, maybe we can discuss later.
Hi, thanks for your nice talk. Mine, I think, is much more a curiosity. When you are studying, we are studying time crystals, usually the time translation symmetry breaking are related to some kind of spatial symmetry breaking also. So I was wondering if there a way to observe these types of oscillations in some other parameters that are not related to these spatial symmetries also?
So here there is no spatial dimension, right? It's a spin ensemble, so there is no notion of spatial structure.
I mean, when you are looking for the magnetization, you are like choosing some direction. So I'm thinking about this kind of spatial symmetry. So usually is this like we are looking for, like if this means is like going up or down and everything. So every time that I saw was something related to some spatial.
Yes, it's basically an emerging symmetry from the model, if I understood correctly this, in the XYZ direction, yes. And it depends on the model and on the interplay between the dissipation that wants to align along Z and the driving that wants to rotate things around X. In space, there is no structure. It's this magnetization axis, the quantization axis is not in the spatial for me. Here there is no spatial structure. You can have if you want, because for instance, the spin systems, they have the discrete time crystals, they have this many-body localization and so on. So you need some structure there and you need the localization to prevent thermalization. But in this ensemble, there is no notion of local structure. So it's not necessary. You can have it.
Just a curiosity on the discrete time crystal. To exist then, you really need many body localization, or just, let's say, late thermalization will be enough because then there is the pulse?
I think there are, so I'm not super expert on the discrete side. I think you need some way of avoiding thermalization. If you
just the pulse. So the question is because in
with a very long time, it's not clear if many-body organization exists or not. So I wanted to know.
But as soon as you have some dissipation, this thing will just decay to some steady state.
Don't thermalize between the two parts.
Yes, but you need everything to be coherent. And therefore, if you have the coherence of dissipation attached to that, like in superquantum quantum computers, the number of oscillations that you will see is finite, okay?
Okay, so let's thank again for Gabriele. Thank you.
E camisa de botão.
Okay, so Fernando de Mello talking about the finite resource measurement process and explication to Wigner's friend scenario.
Yeah. Okay, so good afternoon to everyone. I have to thank the organizers, especially Thaisa, to organize this here in my home institution, so I don't need to show pictures where it is because you know where it is. And also for them to be extremely kind and gentle with me and very patient. And so the last thing is that I've changed the title of my talk, actually changed the talk completely. So I hope you stay cool with that. But that's because we just put these in the archive. So where is it? So I decided to talk about it. And I'll prove to you that it's still related to the topic of the conference. Okay. So just to show you, so that's the quantum information theory group here. That's BPF, Mariana, Mario, and João, who are not here, are master students, and Nina is a PhD student. So I lead the group together with Raul, who is there, and Alfredo is our guru, right? So whatever we don't know, we go there and ask him. But the work that I'll be presenting here today is actually done in collaboration with these guys, Gabriel and Pedro, who are there. Where are they? Ah, there they are. Thiago, who's one of the organizers, Raul again, and Paola, she's the only one who's not here because she's in South Africa now. Okay, so I need not convince you that quantum mechanics is like the greatest theory that has ever been done by humankind. Well, maybe that was an overstatement, but I guess if I downplay a little bit, you would agree, right? And in fact, like next year, we're going to be celebrating 100 years of quantum mechanics. And at the very beginning, so it started as a theory to describe small scales of energy, right? So like hydrogen atom that everyone has calculated once, right? But since then, it has evolved, and now we are using quantum mechanics to describe ever more complex systems, like we as a community have performed 2 slit experiments with molecules which have more than 800 atoms, right? So 10,000 atomic masses. So we've measured quantum correlations between the light of LIGO and the 40 kilograms mirrors that light bounces off. And I mean, it's heavier than my daughter, right? And not very far from myself, actually, right? So, bringing back to quantum information, kind of, so quantum computers nowadays have like hundreds of qubits, right? And PsiQuantum has promised by 2016, 1 million qubits, right? So we are going kind of, we are using quantum mechanics to describe ever more complex systems, right? And that begs to answer the question, I mean, the foundational question that there existed from the very beginning, but I mean, now it's really like a technological imperative to describe, I mean, to decide where we put such boundary, right? So if we believe that quantum mechanics is universal, right? So it has to apply to detector cats and humans, right? But then when do you use the unitary dynamics or the collapse dynamics, right? So that's the old quantum measurement problem. And I hope to convince you that, well, the tools that the quantum thermodynamics community have been using, have been developing, can actually shed some new light on this topic. Okay, and that's the outline of the talk. So I'm not sure if everyone knows what the Wigner-Friend scenario is, so I'll just briefly go over it. And then I show you what are the tools that I'll be using, which are the effective calibration of closed quantum systems, right? And then I introduce this model, this finite resource model of a measurement process. And then I get back to Wigner and his friend and my conclusions. Okay, so let's go. So these pictures were done by, I mean, you may realize the style, right? So it's ChatGPT. I just said, well, create me a picture on Wigner's friend, and that's what came out, right? So I even gave the reference here, so I'm not sure you can see it. But okay, so it's ChatGPT. Okay, so the idea which was posed by Wigner in 1961, is really just a dramatization of the measurement problem, really, right? So there's his friend here who is measuring a spin, let's say that starts on a superposition of plus and minus, right? And her measurement apparatus starts at in the zero state, right? And she's using the description, like the collapse description, right? So the statistics that she collects can be described by these density matrix here, right? So she would say, okay, so half of the time I have the plus state for the spin, and I see the +1 value here in my detector. And the other half, I see the minus state for the spin and the -1 for my apparatus. So this is the state, the spin and apparatus, okay? But Wigner knows a lot of quantum mechanics, so he's describing everything unitarily. And then I say, well, okay, so for me, since everything is unitary, then I'd say that, well, I get this entangled state. So the plus is correlated to +1 and the minus to the -1, but it's an entangled state, right? So the two descriptions are different, and it's no problem. I mean, if they do not communicate, it's not a big problem, right? But they are friends, so eventually they get together, right? And and they are more than friends, they are scientists, so they can think on an experiment that can decide about the two descriptions, right? So let's say that whenever she sees a measurement, a light goes on here and says to Wigner, well, a measurement has been performed, but it doesn't tell him what was the outcome that she saw. Okay. Well, okay. So in that scenario, they can devise a new experiment, so they can measure either phi plus. So it's an observable which has one projector on phi plus and another projector on the orthogonal subspace. Okay. Well, if they do that, then for Wigner, he would get probability 1 to measure phi plus, but for his friend, she would get it like half of the time on. And that's kind of a sort of a contradiction for all interpretations of quantum mechanics, really, right? Because now we have an experiment that two agents kind of disagree what would be the probability that quantum mechanics would assign to this experiment. Oops, okay. Okay, so that's the Wigner scenario very quickly. And one point which is always said is that the main assumption is that, well, you have to be able to measure the spin and the apparatus, right? So, I mean, this measurement here that Wigner is doing, so this here is measuring on the space of the apparatus and the spin, right? And most articles, when this comes along, they say, well, this can be done in principle, right? And that kind of, I don't know, for this community, maybe you kind of get nervous about it. I do, at least. And there's a nice sentence in one of Peter Hyman's nice articles that put numbers on these things, which I find very nice, right? So, in a macroscopic system with all the 10 to 23 degrees of freedom, a small energy uncertainty of 10 to, 10 to minus 10 to 22 joules, still contains 10 to 23 energy levels, right? So that's beyond any precision that we ever will be able to reach, right? So I mean, again, for this community, it's not difficult to remember the discussions between Boltzmann and Loschmidt, right? So if you want to reverse a system, I mean, go there and do it, right? So it's just impossible, right? And actually, this connection can be made even stronger because there is another way of thinking the Wigner paradox, the Wigner-Friend paradox, which is, well, Wigner, instead of making this very difficult measurement, actually he does something else, which is to apply the reverse dynamics on the full system and apparatus, right? So if he reverses, oops, this thing is, if he reverses, so in his description, well, you just get back to the initial state, right? So which was this one here, times 0 for the apparatus. But in her description, if she reverses, I mean, if Wegener is applying the reverse to her description, then she gets like the maximum mixed state for the spin and the apparatus in 0. And then, I mean, the difficult measurement that you had before, now it's a very simple one. I mean, you just measure the spin, and this has been done all over the world, right? So you just measure the spin in these bases, and then you reach the same phenomenon, the same dilemma, right? So here we will see the state plus minus with probability 1, and she will see the state plus minus with probability half, right? So it's the same dilemma. And of course, we are just exchanging like very difficult things to be performed, right? So either you do a very difficult measurement or you reverse a measurement, which is also kind of not very easy to be done. And then again, you can say these sentences. This can be done in principle, right? So that was the point that we start thinking on the connection between statistical mechanics and the measurement process, right? Because I mean, clearly something that you call a measurement should not be reversible. Okay, so that's where the ideas from statistical mechanics are going to come in. And so that's what we're going to do. So describe the measurement process as an effective equilibration process. And I should tell you that there's another group, people from Vienna and Thiago de Barba, who is here also, who is related. They are also pursuing the same direction. Okay? And by doing this, what we are going to be saying is that for all practical purposes, and therefore, like in principle, in scientific theory, in physics, the measurement process is going to be irreversible, right? So I think there is a very strong difference between what one could say when one says in principle in physics and one says in principle in math, right? So that's the main message here. Okay, so maybe you all know this, but I'll just show you like the tools that we are going to use. So these tools from effective calibration of closed quantum systems. And we are going to say that an observable is going to be in equilibrium if it's not very far from its equilibrium value most of the times, right? So here you have the expected value of an operator A, let's say, in a given time t. And here is the expectation value on the equilibrium state. The equilibrium state is just like the average state over all times. And if this value, and this, should I use this? If this value does not change dramatically, like most of the times is very close to 0, so this difference is very close to 0, then we say it's in equilibrium, right? So if your precision is not good enough to see these small fluctuations, then it's for you, it's in equilibrium. So that's what we are going to use. And this can be formally, can be formalized. So, I mean, you can show that the average, on average, so this distance here is not bigger, like the difference between the two square is no bigger than the norm of the operator square over the distance, over the effective dimension, sorry, of the initial state. So here is just normal 1, so it's just like the biggest singular value. And the effective distance is just like the inverse participation ratio in the eigenbasis of your Hamiltonian, but for the initial state. So if your initial state has many components of the energy eigenspace, so it has support on many eigenstates. So this dimension is going to be very big, and this here is going to be 0. I mean, it's going to be very small, right? And therefore, these won't be too far from the equilibrium value most of the times. So that's what this is trying to tell you. So that's the only tool that I'll be using. The rest I'll just show you kind of on the way. And now I give you the model that we've constructed. And as you can see, it's kind of a toy model, right? So, but I think it conveys like the idea and has all the ingredients which are necessary, okay? And it allows also for calculations and numerics, which is also important. Okay, so the model is like this. So it's a magnetization, total magnetization measurement, right? So for the spin, it's the usual thing. So we think it as 1 qubit, which starts in a given superposition of the spin up and spin down. So C plus 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 C minus minus. And the apparatus, we are going to model it as N spins and qubits. Okay, but this space of the apparatus we are going to split in 3 different parts, right? So one which is going to be related to the outcome +1, another related to the outcome 0, and another one with the outcome -1. And these are related to the total magnetization of each of these subspaces. Okay, so the space with +1, which is going to be related to positive net magnetization, is spanned by all the strings which have more zeros, right? So we are going to say that the 0 state has the spin 0, so spin up is going to be plus h bar over 2. So if it has more zeros, then it's going to be related to net magnetization, positive net magnetization. And if it has an equal number of zeros and ones, so it's going to be net magnetization equals 0. And if it has less zeros, then it has negative magnetization. Okay, so these are the 3 subspaces that we are dividing this total space into. And so the dimensions of these guys, well, I mean, it's very simple, right? So the dimension here is just like n choose n over 2, right? And the other one is just like the rest, 2 to the n minus the naught divided by 2, because you have these 2 subspaces. The actual construction of these subspaces are not very important. The important thing is that the limit that n goes to infinity, d naught over d1 goes to 0. So that's the only important thing, right? So I mean, here we could have chosen these subspaces differently, but that's the only thing that really matters in our calculations. Okay, so that's why I'm saying it's like a toy model, and this allows us for making nice calculations and numerics. But that's the only crucial part here, because we could have chosen differently. So the initial state then is going to be, well, so it's just the pure state for the spin, and since the apparatus starts in the 0 value, the only thing that we know is this macroscopic value. So we take the microcanonical state on this subspace related to the 0 magnetization. We could have chosen also pure state here and a sample over these pure states which have magnetization 0, but these would lead to exactly the same thing. But that's, I think, it's the most sensible choice. Okay, so for the Hamiltonian, then we are going to choose the following one, which is like a standard Hamiltonian for measuring things. So the plus on the qubit side will be related to a Hamiltonian, which brings excitations from the 0 subspace to the +1 subspace, right? And the -1 is related to a Hamiltonian, which brings excitations from 0 to the -1 subspace, right? And the idea is that since the D1 is going to be much bigger than D naught, oh, sorry, the other way around. So yeah, no, that's correct. So D1 is going to be much bigger than D naught. So everything that starts on the subspace 0 goes to the subspace, which is much bigger, and then there is going to stay there. So it's going to thermalize there. And so what we do is we take these Hamiltonians here from the Gaussian unitary ensemble, and that's because, well, I didn't say it precisely, but for these theorems to hold, the equilibration theorems to hold, we need the Hamiltonians to not have degenerate gaps, and therefore, by doing this, I'm sure that there are no degenerate gaps. But it's going to be fixed, but we just take one instance of a GUE matrix, but then from there on, it's fixed, okay? It's just to guarantee that we don't have degenerate gaps. Okay, so, but then we are assuming that this here is a macroscopic object, and therefore there's no way for you to exactly know the Hamiltonian of this apparatus, right? So, and therefore we just include some perturbation, and in the same form as we had before for the Hamiltonian, for the bare Hamiltonian, so the H0 Hamiltonian. So it still connects the correct subspace, right? So because we are assuming that the only part that is, which has some randomness is the apparatus, so we just put this part here as perturbation. And for this one, we also, again, take from the GUE ensemble, but then in every round, we assume that this is a different matrix, okay? Because we don't know what's the actual Hamiltonian. I guess someone was talking about not knowing the Hamiltonians exactly yesterday afternoon as well, right? Okay, so that's it then. So that's the model. And then I get to see how the probabilities on these this model go. So if I have fixed one Hamiltonian and one perturbation, so using this theorem that we've used, that I've shown, I mean, we see that the value at each time is not far from the equilibrium value for most of the times, right? Because then we get something which goes kind of decays exponentially here. So the difference between the probability at each time with the average probability is very small for most of the times. So it equilibrates, that's what I'm saying. The probability equilibrates. And that's what you see here. So here's, again, it's one fixed Hamiltonian H0, and I take three different values for the perturbation. So here's for if my apparatus has 2 qubits, which is not very good apparatus, you see that it oscillates a lot. But then if you start increasing the size of the apparatus, then it starts to equilibrate, and then you see for n already equal 8, then you see that fluctuations are very small. So if your precision is smaller than it's not very great. So if it's bigger than this, so it's like this ball here, so you actually don't see any fluctuation anymore, right? But the values, the equilibrium values might actually change for each choice of Hamiltonian, H0 and V. So these now, we use Levy's lemma to show that, well, these values are actually typical if you have very large apparatus. So the equilibrium value is very close to the typical values that you get for any Hamiltonian H0 and V. So here's the average over the Hamiltonians and the perturbations also. So what we're saying is that these values here are actually typical. And that you could see also from here, because you see that these three different lines that we have here are the equilibrium values for the probabilities. Oosh. And here you see that they all coalesce to a single one. At least on this scale, you cannot see the difference between them. Right. Okay, and moreover, these values we can actually calculate, and the value that we get is this one here. So it's C plus minus, depending on what you're measuring, square on a ratio which depends on the dimension, times the ratio which depends on dimension. So if you chain all this together, so you see that for each choice of H0 and V, the probabilities of plus or minus 1 are not very, are very close most of the times to the probabilities that you have, the equilibrium probabilities. And these values are actually very close to the typical values if the apparatus is large and for large times. And that's the value here. And if the apparatus is large, so D1 is much bigger than D0, and then you get your textbook probabilities, right? So the other thing is like the measurement dynamics. So that's I guess the biggest difference from the decoherence programs, let's say. So here we are assuming that the perturbation is not known. So therefore, in each round, the best thing that I can say is actually taking the average over the perturbations, right? And we follow the same strategy as for the probabilities. And then we show that this state here is very close to the typical state when you take averages over the Hamiltonian and the perturbation. And that's what's shown here. So we are calculating the distance in time from the state which describes the dynamics, so the state at time t, and to the average state on time and on the Hamiltonian and the perturbation, right? And here, so in yellow is the n equal 4 case, and then green n equal 6, and then n equal 8. And then these two lines here for n equal 4 are two choices of Hamiltonian H0, right? And there are two choices also of Hamiltonian H0 for n equal 6 and also for n equal 8. But then you see that for large n, actually this difference disappears. And when they are thermalized, so there is no difference between the states. So the state at time t actually is very close to the typical state, to your fully average state, so in time and Hamiltonians. And actually, this state can be calculated, right? So we can take these averages analytically, and that's the state, and that's what you would expect, I'd say. So the plus state is connected to something in the apparatus, which is just the microcanonical. On the plus one subspace, the minus state is connected to something which is the microcanonical on the -1. And then there is this kind of error here, because it's a finite resources, right? So I mean, there is still the possibility of measuring 0. Right? But if you make n large enough, then this probability goes to 0, and you get exactly, again, the textbook states, right? So it's C plus mod C plus square for the plus, and the state of the system of the apparatus on the plus, and C minus square, and the state of the apparatus on -1. And so just reading out, so the outcome plus then happens with this probability that goes to C plus mod C plus square in the limit of n big, and the post-state measurement would be this one here, and you can read out all the other states. And one thing that should be said is that these are not stationary states. So if you now start from this state, actually evolves, right? But again, in the limit of large n, so these are quasi-stationary states. And the last point is about the irreversibility of this measurement, right? So here is just the distance between the initial state and the state that you go with the Hamiltonian plus 1 perturbation, and then you go back with the same, the age not Hamiltonian, but you go back with a different perturbation, right? Because you don't know the perturbation. And so that's the difference. And then you see if you increase this parameter, which is like the controlling the perturbation strength, so very quickly you don't go back to your initial state, so which would be distance equals 0, right? So very quickly you go to very large values of the distance. So remember that trace 1 distance goes up to 2. Right. And here is one specific point in time, one specific point here of epsilon. So here's n equals 6. So you see that from here to here, I'm evolving forward with 1 h naught and 1 v. And from here on, I get back. I try to reverse this, but with a different perturbation. And then I don't get back to the beginning, right? Which is sort of expected if you don't know the Hamiltonian. It has to be irreversible. Okay. Oops. I'm almost finishing. So just to get back to Wigner and his friend, so if they are both using this model, and Wigner is really trying to describe a measurement, so he doesn't know the unitary that is describing. I mean, there is no unitary describing the measurement apparatus, so they would both say the same thing, which is just this state that I've just shown you, and therefore they would reach some agreement. And just to show a picture of Wigner, who is here, and possible friend Heisenberg, who is here. Right. They are not Legos. And to reach my conclusion, so what we did was to introduce a quantum measurement model that accounts for imprecision of macroscopic systems, right? So our model recovers the kind of the usual, the expected results for large apparatus and long times, right? And in this framework, so the collapse is just a very effective and very useful description of the unitary dynamics, or of a closed dynamics, right? And so no contradiction is reached in the so-called Wigner's friend scenario if they are both using a finite resource model of the measurement process. So the article is there, and I'll be happy to answer any questions that you have. Thank you for your attention.
Thank you, Fernando.
Obrigado, Fernando.
Questions?
Interesting thoughts, thank. Do you think it's a safe assumption to assume that the apparatus is a small perturbation on the state of the system, like on the Hamiltonian of the system?
I'm not sure I understand the question. I mean, what we did was, it's not, what we're saying here is to say that we don't know the Hamiltonian very well, right? So there's a part that we do know. Oops, sorry. How is this? Yeah. There's a part that we do know. I mean, when we construct an apparatus, we should know what we are doing, right? And but there is another part that we don't know because.
Okay, I thought that was the interaction of the apparatus with the system.
No, I mean, this here is the full Hamiltonian, right? So V contains the parts in the spin and also on the apparatus, and for both cases actually, right? So we are just saying that the Hamiltonian is not well defined, so we cannot know, I mean, the position of all the electrons and all the Coulomb interactions of everything, right? So there is always an uncertainty. That's the number, these mind-boggling numbers that I showed before, right? So it's 10 to 23 energy levels and a very small uncertainty.
But what is actually measuring the system isn't exactly what, like how the apparatus is interacting with the system. Like it's only the part of the apparatus that interacts directly with the system.
Yeah, well, I'm not, as I said, I mean, here's the interaction, right? So there's interaction between the spin and the apparatus, and here as well. How do I go back? So here as well. So it's an interaction, right? Actually, I just shown you interactions. I mean, there is no free dynamics. I mean,
sure. Right? I think I'll.
Okay. Okay. Yeah. Thank you. Marcelinho.
Yeah, Fernando, thanks for the talk. Very nice talk, except maybe for stealing the toys from Nada.
Yeah,
that we have to discuss later.
Yeah, that's right.
Anyway, so when we discuss this and when you give the talk, you use the sentence, it's just that we don't know the Hamiltonian of the apparatus, but that puts too much pressure on us. Can I rephrase it in the sense that, like, whichever apparatus you choose, the internal structure of the apparatus itself, just that, will make it so that when it interacts with your system to make the measurement, it will be in a different configuration anyway, in such a way that this interaction itself will be undetermined when you go to repetitions, in the sense that this time it's a particular structure, next time it's going to be something slightly different, so on and so forth. Can I rephrase it in this way?
Yeah, I mean, so for you that don't know, Marcel and I and Roine, we drink beers every Thursday, and we always have this discussion. And I always have a problem with this sentence, which is, it exists, but I don't know, right? It's always kind of complicated sentence for me. So, okay, of course, like, I don't know. So at some point, when there is interaction between the spin and the apparatus, maybe, okay, so I'll just go in your flow. So there is some Hamiltonian which is describing interaction, but for you, I mean, for us, the only thing that you can actually say is that the average description, right? Because there is no way, I mean, there is no way to know it, right? Because the resources that you need are really kind of ridiculous, right? And that's the idea, right? So the amount of resources is ridiculous. So therefore, the theory has to take this in account, and the best that you can do is to take average over V. So my point is, this is a single shot description. For every shot, that's your best shot. For every shot, that's your best guess.
So you mentioned something. How this approach of yours compares, because you're saying that you have a part of the Hamiltonian that you don't know. How does that compare when people, in the usual decoherence picture, that people put a stochastic thing or an open systems thing? My specific doubt is, you compare unitary with non-unitary descriptions. Is your description unitary the whole evolution, the time evolution? There is a period of time before full equilibration where there is some non-unitarity, or is unitary in the sense that this Hamiltonian that you don't know is unitary, but at the same time, there is a piece that's missing? Can you?
Yeah. Well, maybe I'll try to disentangle that. So the point is, so the whole dynamics is described by this average, right? So we're taking averages over unitary dynamics. And therefore, so any pure state will not evolve will not remain pure, right? And that's the main difference, I'd say, from the decoherence program. So the decoherence program is, so that's again, we were discussing the other day. So you can think, for instance, your initial state of your system is pure, and then there's the environment, which is often put in an equilibrium state. But you can always purify this thing, right? And so if you purify this thing, then you have a a well-known unitary, right? And then you apply this unitary and the coherence says, okay, so, but I don't have control of all my degrees of freedom, and then I trace part of it, and then I get a mixed state, right? But you see that the state at time t is actually a pure state. So that's an ignorance that you decide to have somehow. Here is different, right? So it's maybe a small difference, but I think it's conceptually important, which is there's no way for you to write the state at time t. Even if you start with your pure state, so you purify you have your system, your spin in a pure state, and you purify the apparatus state, which, okay, you may do it, right? But then at time t, the best that you can say, since you don't know the Hamiltonian, is this thing here, right? So there's no way for you to write a specific wave function for the state. So that's the difference. So ignorance is built in here, so to say. So it's not that I'm deciding to be ignorant. So here is kind of built in, right? So that's the main thing. I'm not sure if I answered. No, I mean, there's only this part here. So it's always non-unitary if you want, because here we are taking average over the perturbations.
Okay, it's a different question. So my understanding is that your theorem works. You've asked for an Hamiltonian that is non-degenerate and with non-degenerate gaps. Now, if you look at many body systems, you often have degeneracy. If you just think about phonons, you will have, repetition of gaps. So what happened in this case? Do you have an idea? Everything broke down, or you just didn't work out the theorem? Or, yeah.
Sure. Yeah, thank you. Yeah, I mean, all these theorems, which were done by various people, maybe some people here actually. So there are always the versions where you take into account degeneracies. So you can account for a small number of degeneracies. But I'd say, you correct me if I'm wrong, that whatever Hamiltonian of an apparatus, I mean, this is going to be a very complicated thing, right? So the chance to have exact degeneracies are very, very small, I'd say, right? So degeneracies would imply some kind of commutation relations, right? So some symmetries, really, right? So I'd say that these are very improbable in a macroscopic system. So one would have to craft something very specific, I'd say. No, I see some people disagreeing. Yeah, so I'm describing the apparatus as a quantum system. Yeah, so that's why I took this. Yes. Oh, I see. No.
Okay,
Sorry.
Perhaps we can leave the questions.
Sure. So maybe just to answer that one. So the Hamiltonian for the system, I mean, that's the full Hamiltonian, right? So the system part is here. So what I'm asking to be non-degenerate and not having degenerate gaps, just a single qubit. Yeah. So the apparatus and qubits, and this Hamiltonian here has to not be. I mean, in our case, we assume that this has no gaps, no degenerate gaps, and no degenerate gaps, and no degeneracies and no degenerate gaps.
Yeah,
Sure.
I think you can
Sorry,
talk a bit later in the cocktail. So let's thank again Fernando.
Works. Okay. Which one is the pointer?
The first one.
Okay. All right, everyone. As you can see from the title, I'm going to be talking about the connection between fluctuation theorems and thermodynamic uncertainty relations. So I'm going to start with a quick overview of these two types of results. Then I'll talk about some known results in the literature where we start with fluctuation theorem and we derive a thermodynamic uncertainty relation. Then I'll start talking about the results of this work here. What's the main idea behind this family of thermodynamic uncertainty relations? And then I'll finally show this thing in practice in a physical example where we can use the Tasaki-Crookes fluctuation theorem. Okay, so the motivation is that when you're working with system that's far from the thermodynamic limit, you look at currents like heat, work, and reproduction, and you don't see a smooth evolution in time. You see a very noisy one. And it points that not only the averages, but the fluctuations matter a lot in this case. So if you want to get a clearer picture, you need to turn to results that talk about distributions, not just averages. So we have things like fluctuation dissipation relations, the fluctuation theorems, and the thermodynamic consistency relations. I'll be focusing on the last two. So first, the fluctuation theorems. The idea is that you are relating the statistics of two different types of processes. We have one process that are called the forwards process, another one that is the backwards process. And the idea is that the backwards process is a kind of time reversal of the forwards process, in the sense that the interactions are happening in the opposite order, but the starting state of one is not necessarily the final state of the other. So for example, we could have a system starting in a thermal state and interacting with a bunch of ancillaries in a particular order, and my backwards process could be the same system, also in the thermal state, interacting with the same ancillaries, but in the opposite order. Another important example is when we have an external forcing, so we could consider as a backwards process, starting with the same situation, but with the forcing reversed in time. From a mathematical point of view, fluctuation theorem looks like this, where capital sigma is the entropy production. And there are many different versions of these fluctuation systems where we use different variables and more complicated things. But the gist is that you always have the probability of something happening in the forwards process divided by the probability of the opposite thing happening in the backwards process. And this is going to be equal to your exponential of the entropy production. We can use these to derive the second law of thermodynamics in a statistical sense, and we can associate these fluctuation theorems to any relation of the form average of exponential of minus sigma equal to 1, where sigma ends up taking the role of your entropy production. There's a lot of famous fluctuation theorems described in the literature. For example, we have Jarzynski's equality that is related to the fluctuation theorem I just showed. An example using a different variable, not just the entropy production, is the Crookes fluctuation theorem, where now we are talking about a distribution of work, but the thing that shows up in the exponent is still the entropy production. And these ideas have been generalized to more complicated situations. For example, when we have feedback control, we have the Sagawa-Ueda fluctuation theorem. We can generalize these things to Bayesian networks and even more exotic setups. Now, the second type of result that I'm going to be concerned with is the thermodynamic uncertainty relations. And these are relations that give me a lower bound for fluctuations in my system in terms of averages on my system. So these relations that I'm just going to call TORs for short, they were first discovered by Barato and Seifert in a situation of a non-equilibrium steady state of a classical Markovian system. They are given by this inequality here. Here phi is some current that you are measuring in your system, and capital sigma is again the entropy production. Now, once we know that this type of relation holds in a classical system, a natural question is, what about fluctuation theorems? And it turns out that if the gradient that is creating your current is small, then you can derive a very similar relation with just a slightly smaller bound. The point of these relations is actually that you're kind of establishing a trade-off between different things. For example, if you keep your current output fixed, but you want to reduce the fluctuations you see in your current, you can see from the inequality that after some time, you're going to have to start increasing your dissipations, and vice versa. If you want to decrease dissipations with a fixed current output, you will need to start increasing your fluctuations after some point. If you think about this in the context of a thermal machine, this becomes a trade-off between power output, power fluctuations, and efficiency. And the point is that you can't have at the same time a high power output, low power fluctuations, and high efficiency. You can have at most two. Because if you have low power fluctuations, this term vanishes. If you have high efficiency, this term vanishes, and the product bounds the power output. Now, these TORs that I talked so far, they have very clear limits of validity. You either need to be in a classical system or you need to be in a situation with small gradients. So if you start to dig a little bit deeper, start seeing violations of these TORs. And this is what's happening here on this graph, which can be found on this work here. What we have here is a chain with 13 quantum dots where the interactions have been fine-tuned, and on the edges of each the chain, you have two baths that have the same temperature, but there is a voltage difference between the two, and this induces electron current. And what we have here on the x-axis is the size of this voltage difference, so the size of the gradient that is creating your current. And on the y-axis here, you have a measure of fluctuations that's adimensional, and it's pretty much the result of just taking everything here in the classical TOR, moving to one side except for a constant. So it would be the variance of the current times the average of the entropy production divided by the square of the average current. So the point is that the classical TOR tells us that this quantity should be larger than 2, so above the gray area. So this doesn't happen, but no problem, this is a quantum system. And the quantum TOR tells us that this should be larger than 1, so above the orange area. And we can see that for small gradients, this is respected, but if you start to increase the gradient, violations become possible. And this highlights one of the important points of finding TORs that are derived from other things that are hold in more general settings like fluctuation theorems. This would lead to quantum generalizations that should hold even in the limit of high gradients. Now, some results where we find fluctuation thermodynamic uncertainty relation from a fluctuation theorem include these two. The first one is something that holds for what I'm going to call a symmetrical fluctuation theorem, which is a situation where the forwards and backwards processes are the same. They have the same statistics. This one was obtained using an optimization approach, and a natural consequence of this is that you can saturate this bound. So for every choice you have of the current phi and a positive choice for the average of the entropy production, you can find a setting where equality holds in this inequality. The second example, on the other hand, works for a general fluctuation theorem. So we are in a situation where the averages and the variances of the two processes are not necessarily the same. So this measure of fluctuations that we use here needs to be adjusted. And the same thing happens in the bound. We can see that the bound depends on both processes. But the point is that these two relations still keep the spirit of the original TOR, because what you're doing is you're finding bounds for the fluctuations of your current in terms of something that depends only on the entropy production and decreases as the entropy production increases. This is pretty much the recipe that gives you the trade-offs we had. Now, more recently, this work here looked at averages of functions of the entropy production in order to get a similar bound. And I found this, which holds for the case of a symmetrical fluctuation theorem. And the idea that I'm going to explore here on this work is that we can use this idea of going beyond first moments in order to find a fluctuation theorem that can be saturated and works for an arbitrary fluctuation theorem, not necessarily a symmetrical one. Okay, so the way that we do this is that, well, first I want to find a TOR, so I want to find a bound for the variances. But I also want to have something that works for an arbitrary fluctuation theorem, so the two variances are not necessarily the same. To keep things flexible, I'm just considering a convex combination of the two variances. Like the other TORs, I want to use as information the averages of the current. And in order to access the higher order moments of the entropy production, I'm going to assume that I know all of the marginal distribution of the entropy production. The first step is to rewrite everything in terms of the forwards process. So you can start with your variances and show that bounding the variance is equivalent to bounding this expectation. And you can also rewrite your current in the backwards process in terms of the forwards process. You can then phrase your problem like this. You want to find a bound for this in terms of all these informations. But the point is that I want to actually solve these related problem here. That is the following. Suppose you have your process there, you have your current phi and your entropy production sigma. So you're going to have a joint distribution of these two things because they are connected to measures that you're doing in your system typically. So given this joint distribution, I want to find the function f that minimizes this subject to these two constraints. And this is useful because first, phi is a function of sigma and phi that obeys the same constraints. So whatever this minimum is, it will give me a bound for that. But as I'm going to show here, the result for f depends only on the entropy production and of the two averages. It doesn't even depend of the joint distribution itself. And as I'm going to show, this leads us to a situation where we can saturate the bound by simply swapping phi for f in your distribution. Now, the way we do this is that we start by defining a functional for the expectation I want to minimize and some functionals for the constraints I want to impose. And we just use calculus of variations. We take some functional derivatives, use Lagrange multipliers, and we get to this equation here. And we can see this in this equation that either p is 0 or the thing in parentheses is 0. So what's happening is that that function that minimizes everything is given by this on the support of my original distribution. But since it really doesn't matter what f is outside of the support, I can just assume that f is equal to this everywhere. Now, to finish finding what f is, we need to find the two Lagrange multipliers. We do this by imposing our constraints. And then, as I said before, phi is a function of sigma and phi, obeying the same constraints. So we're going to have this inequality. And we can see here very clearly that if I just use f instead of phi, and this can be done because it can simply define my backwards process like this, we end up with a situation that has the same expectations and can be saturated. Now, we can do some algebra and turn that bound for expectations into a bound for fluctuations. We can define an adimensional measure of the fluctuations of my current given by this. And it's something that is very similar to the Potts-Samuelson bound that I showed a few slides ago, the other TOR for an arbitrary fluctuation theorem. And we have the same structure. We have here fluctuations in my current that are being bounded by a kind of complicated thing, but in the end is something that only depends on averages involving my entropy production. And it's a bit harder to see, but it's something that decreases as the entropy production becomes larger. The case alpha equals 0 needs to be done separately here because of a technical difficulty, but you end up getting pretty much the same result in the sense that it's still a bound for fluctuations in terms of only the entropy production. Now, one thing that, let me go back here before going back. One thing that I want to call attention here, it's something that's kind of interesting, is that if you see the way that the averages show up here, it doesn't depend on this parameter alpha, which is pretty much interpolating different bounds in this family. And it's also the same way that this shows up in the Potts-Samuelson bound. And there's a deeper reason for that. To see this, we can investigate this covariance here. If we expand this, we see that we have an average of a product minus a product of two averages. If we recall a few slides ago, the thing in red here is essentially the current in the backwards process. And this average here of the exponential of minus the entropy production is going to be equal to 1. So this covariance is pretty much the sum of the currents in the forwards and backwards process. So you can actually rewrite that bound in terms of this covariance, and this gives us some funny conclusions. For example, if the current and the entropy production are independent from each other, this bound tells you absolutely nothing. It just tells you that the variances are not negative. But that's not actually a weakness of the bound, because if you have no covariance, This means that you can satisfy all of the average by just making phi be one constant in the forwards process and be minus that same constant in the backwards process. And in this case, it's pretty obvious that there are no fluctuations. So what's happening here and also in the Potts-Samuelson bound is that the existence of these TORs is intrinsically connected to the existence of correlations between the current you're measuring and the entropy production. If there are no such correlations, then you can't say absolutely anything in this situation with a general fluctuation theorem. And I suspect that this should be true for any TOR derived from an arbitrary fluctuation theorem. Okay, we have 8 minutes. That's enough time. Okay, so now to the final part. I'm going to show here how this thing works in practice in a physical example where we can use the Tasaki-Crookes fluctuation theorem. The setup I'm going to use is really a very dumb model just to make the calculations. The idea is that you have a two-level system here with a time-dependent Hamiltonian given by this matrix here. And we have a bath at time temperature T, and I'm going to weakly couple the two-level system and the bath for some length of time Tf. And this is going to be my forwards process. For my backwards process, I need to think about this Hamiltonian as being some kind of external forcing acting on the two-level system. So what we have to do is use the exact same setup, but using a Hamiltonian that is reversed in time. So this is going to be my Hamiltonian for the backwards process. We can see that if I take the interaction time to be in this interval, the two Hamiltonians will be different. So the two forward and backwards processes are going to have different statistics. Now, the next step is that we need to use equilibrium states for both the starting states of the two processes. And I'm going to use the same temperature as the bath to keep things simple. We need to define our free energy difference like this, or entropy production like this. And since I'm weakly coupling the system and the bath, I can calculate the work distributions by just looking at the characteristic functions, which can be obtained by this expression here. Now, if you put all of this together, everything just fits, and you end up getting the famous Tasaki-Crookes fluctuation theorem given by this. And this is what it looks like. Now, we have many different bounds here. If for each value of alpha between 0 and 1, we end up getting a different bound. So the first thing I'm going to see is how these bounds compare for different values of alpha. In this example here, I'm using these parameters for the Hamiltonian interaction time and temperature. And the quantity in my bound is given here by the orange curve. And the fluctuations that I am trying to bound given by this, and since the next slides are going to be pretty cramped, I'm just going to write this as epsilon alpha in the next ones. They're given by the blue curve. And the only thing that the QR tells me is that the blue curve is above the orange one. But we can still look at here and see that here it's looser, here it's tighter, etc. Now, this might give you the wrong impression that, we should just pick alpha equals 1/2. But it turns out that there is no consistent alpha that always gives you the tighter bound. This is something that depends on the problem that you're dealing with. It just so happens that it's a little bit more than 0.5 in this case. Another thing that we can do is that we can compare this TOR with other bounds that already exist. Since I want something that needs to be applied in an arbitrary fluctuation theorem, this pretty much means compare with the Potts-Samuelson bound. In that bound, we are using the sum of the variances in the forwards and backwards process. So in order to make the comparison, we need to use alpha equals 1/2. And one thing that's funny about alpha equals 1/2 is that the bound simplifies a lot and it becomes this. And if you have a very good memory and recall some slides ago, this is exactly the same bound you would get if you had assumed that you had a symmetrical fluctuation theorem right off the bat. But I think it's kind of a coincidence. Maybe there's something deeper here. I don't know. Okay, what I'm doing here is I'm changing the temperature of the bath and the starting states. The fluctuations I want to bound are given by the blue curve. This new TOR with alpha equals 1/2 is given by the orange curve, and the Potts-Samuelson bound is given by the green curve. Another thing that we can change is the interaction time. And here, in this case, the fluctuations and the bounds, they oscillate a lot. So it would be just a hot mess if I had tried to plot this here. So what we have instead here is the ratio of the fluctuations to the bound. Now, the ratio for the Potts-Samuelson bound is given by the orange curve, and the ratio for this TOR is given by the blue curve. And the dashed line is the situation where the fluctuations would saturate the bound. So we can see that for this TOR, this is happening for the case of short interactions. Okay, that was everything. I'm just going to sum up everything that we did here. That is that we have here a TOR relation that should work on any situation where we have a fluctuation theorem. A few caveats. It's a fluctuation theorem that needs to be for real distributions, or at least a quasi-distribution where everything's positive. If you put anything negative there, the whole thing just crumbles, so don't try it. But in any situation where we have a fluctuation theorem like that, this should hold. You should have this relation between your fluctuations involving the forwards and backwards process and your entropy production. Because of the optimization-based approach, we can find setups where these can be saturated. I can't promise anything about the physicality of the settings where they are saturated, but they exist at least mathematically. And something that's funny that I also can also connect to the Potts-Samuelson bound is that there seems to be an intrinsic relation between the existence of correlations and the existence of TORs in the setup of an arbitrary fluctuation theorem. For alpha equals 1/2, we can find comparisons with other TORs that I did in the case of the physical system. And one final question that I think is still interesting that could be approached here is whether or not we can find a TOR that works for an arbitrary fluctuation theorem, can be saturated, and just use first moments, because the first moments are easier to connect to dissipation instead of these crazy averages of complicated functions of entropy production that we're using here. This is a bit more complicated to relate to direct dissipation. And I think this result should at least give some clue of how to do that. Okay, I would like to thank the organizers for the opportunity to present. I would like to thank everyone that's still awake at the end. And these are the references that I used throughout the work. This is the preprint for this work, the papers about fluctuation theorems I talked about, the ones about TORs, the ones about violations, and the one I used for the work distributions.
Thank you, André. Questions?
Hey, Chimpa. So these TORs, they, I guess, hold for like finite processes, not for steady state, right? Because for steady state,
if you find a fluctuation theorem for your steady state, it should hold. It can be on one shot, but it's kind of the other TOR fluctuation we had found, which you're just using pretty much the mathematical structure of the fluctuation theorem.
I don't think that's the problem, because there will be fluctuations theorems for the steady state, but the problem is that the variance, the bound trivializes usually. It becomes just variance larger or equal to 0 because the variance doesn't go as t squared, it goes as t. So actually my question would be, since you're using more complicated functions of the entropy production, it's not only the first moment, would it be possible maybe to think about some functions that scale differently with sigma in the large sigma limit? That's pretty much the question. It says you need to have a bound that behaves differently for large sigma. And then it would work for steady state possibly.
Yeah, I don't know if you can get that from here, but if it seems to be something that could be thought about. Okay, we can talk later.
Questions? Okay. I think that it's time for the cocktail, right? So let's thank
Yeah,
you again.
let's go.
André. Thank you. So just two fast announcements. So we have now the cocktail with the poster session. But before, we are going to make a group photo for the workshop, also in the garden there, everybody together. Okay.